The universe is exactly the size it needs to be to trap us. 93 billion light-years across. That is not a guess. That is not a rough estimate rounded for convenience. It is the measured diameter of the observable cosmos, calculated from decades of data, confirmed by multiple instruments, accepted by every major observatory on Earth. And when you take the total mass of everything inside that space, all the stars and galaxies and dark matter and energy, and you run it through the equations that define a black hole, you get a number back, a single number that should mean nothing, the Schwarzschild radius. The point at which gravity becomes so strong that nothing, not even light, can escape. For our universe, that radius is 93 billion light-years, exactly the size of the boundary we are sitting inside right now. This is not a metaphor. It is not a coincidence that breaks down when you do the real math. It is the math. The same equations that predict the event horizons of black holes, that describe how space-time bends around massive objects, that have been tested and verified 1,000 different ways, are telling us something deeply uncomfortable about where we are. The Hubble expansion rate, the thing that measures how fast the universe is flying apart, matches the geometry you would expect from the inside of a black hole. The Big Bang, that moment we have always called the beginning of everything, sits in the equations exactly where an event horizon crossing would sit. And if you follow the implications all the way down, the possibility emerges that every black hole in our universe might be doing the same thing, creating new space, new time, new universes born from collapse, stacked inside one another in an infinite chain we cannot see and cannot escape. This is that idea, and the math refuses to let it go. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The observable universe is 93 billion light-years wide. That number gets repeated so often in documentaries and textbooks that it has lost its ability to shock. It rolls off the tongue like a polite statistic, something you nod at and move on from. But stop for a second and actually think about what that means. 93 billion light-years, not miles, not kilometers, light-years. The distance light itself, the fastest thing in existence, travels in a full year, and not just one of those distances, 93 billion of them. You can't picture it, nobody can. The human brain did not evolve to hold numbers like that. We are pattern-matching machines built to track predators across a savanna and estimate whether we can make it to the next watering hole before dark. We are not wired to comprehend structures so large that light takes longer than the entire age of recorded human civilization to cross a fraction of a percent of their width. But here is the thing that should bother you. The universe is only about 13.8 billion years old. So if the Big Bang happened 13.8 billion years ago, and nothing can travel faster than light, then the farthest we should be able to see in any direction is 13.8 billion light-years. The math is simple. Time multiplied by speed equals distance. Light has had 13.8 billion years to reach us, so the edge of everything we can observe should be 13.8 billion light-years away. The observable universe should be 27.6 billion light-years across at most, not 93 billion, not even close. Except space itself has been expanding while that light was traveling. This is not a detail. This is the entire reason the numbers don't match. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is now. Over the billions of years it took for the light to complete its journey, the space between us and that galaxy stretched. The galaxy kept receding, the photons kept flying, and by the time those photons finally arrived at Earth, the object that emitted them was no longer 13 billion light-years away. It was more than 40 billion light-years away. The expansion carried it there while the light was in transit. So the observable universe is not defined by how far light has traveled. It is defined by how far away the objects are, now that emitted the oldest light we can see. That distance, in every direction, is roughly 46.5 billion light-years. Double it, and you get 93 billion light-years as the diameter of the observable universe. A sphere of space centered on Earth, containing every galaxy, every star, every photon that has had enough time since the beginning of the universe to reach us. That is the edge of what we can see. Not the edge of the universe itself, just the edge of the part we have access to. Beyond that horizon, there is almost certainly more universe, possibly an infinite amount more, but we will never see it. The light from anything farther away has not had time to reach us yet. And because the expansion of space is accelerating, some of that light never will. There are galaxies out there whose light is currently en route to Earth, but which are receding so fast that the photons will never close the gap. They are running on a treadmill that is speeding up. This is already strange. The universe you can see is not the universe you live in. You are standing inside a bubble, and the walls of that bubble are not made of matter or energy. They are made of time and geometry. You cannot break through them. You cannot peek over the edge. You are confined to a region of space not by any physical barrier, but by the simple fact that information from beyond a certain distance has not arrived yet, and in some cases never will. Now here is where it gets worse. Take the mass of everything inside that observable universe. Every galaxy, every star, every planet, every atom of gas drifting in the voids between galaxy clusters, every photon, every neutrino, all the dark matter we cannot see but know is there because of the way it bends light and holds galaxies together. Add it all up. The estimates vary depending on which model you use and how you account for dark energy, but a commonly cited figure for the total mass of ordinary matter alone is about 1.5 times 10 to the 53rd kilograms. That is a 1 followed by 53 zeros, in kilograms. For context, the Sun weighs about 2 times 10 to the 30 kilograms. The observable universe contains enough matter to make roughly 10 to the 23 suns. That is 100 billion trillion suns, and that is just the ordinary matter. Add in dark matter, which outweighs ordinary matter by a factor of about 5 to 1, and the total mass climbs higher. Some estimates, when you fold in the equivalent mass energy of everything including the contributions from dark energy and the energy locked in the fabric of space-time itself, push the number even further. Now take that mass and plug it into an equation. The equation is called the Schwarzschild radius formula, and it calculates the size a black hole would be if you compressed a given amount of mass into a small enough space. The formula itself is simple. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. You do not need to follow the algebra. What matters is this. If you take the total estimated mass energy of the observable universe and run it through that formula, the Schwarzschild radius you get is roughly 46 billion light-years. The radius of the observable universe is roughly 46 billion light-years. The Schwarzschild radius for the mass inside it is roughly 46 billion light-years. Those two numbers match. Not sort of, not in the same ballpark. They match within the uncertainties of the cosmological models we use to estimate the universe's mass and size. That should make you uncomfortable. The Schwarzschild radius is not just any radius. It is the defining feature of a black hole. It is the distance from the center of a black hole to its event horizon, the point of no return, where space-time is warped so severely that nothing, not even light, can escape. Cross the event horizon of a black hole, and every direction you try to move leads inward. The future itself points toward the singularity at the center. Escape is not difficult, it is geometrically impossible. A black hole with a Schwarzschild radius of 46 billion light-years would have an event horizon roughly 93 billion light-years across, the same size as the observable universe. Now, you might be thinking this is a coincidence, a quirky bit of numerology. After all, the observable universe is not collapsing. Galaxies are not falling towards some central point. Space is expanding, not contracting. We see distant galaxies moving away from us in every direction, not spiraling inward like water down a drain. On the surface, the universe does not behave anything like a black hole. But the numbers do not care about your surface-level intuition. The numbers are sitting there, quietly, waiting for someone to explain them. And so far, no one has delivered an explanation that makes the coincidence go away. Let's be clear about what the Schwarzschild radius actually tells you. It is the radius at which the escape velocity from a spherical mass equals the speed of light. If you are standing at that radius, you would need to move faster than light to get away. Since nothing can move faster than light, you cannot get away. That is what defines an event horizon. Now think about the observable universe. You are sitting inside a spherical region of space roughly 46 billion light-years in radius. Beyond that boundary, there is more universe, but you cannot see it. Light from beyond that distance has not reached you, and because space is expanding, some of that light never will. You are confined to a bubble, not by a physical wall, not by a force field, by geometry. By the structure of space-time itself and the finite speed at which information can travel through it. You cannot leave your observable universe. You cannot see beyond its edge. You cannot send a signal past its horizon. You are, in every practical sense, trapped inside a sphere from which no information can escape outward to regions beyond your particle horizon, and from which no information from those regions can reach you. That starts to sound a lot like an event horizon. To be very careful here, the particle horizon that defines the observable universe is not the same thing as an event horizon around a black hole. The physics is different. A particle horizon is a consequence of the finite age of the universe and the expansion of space. An event horizon is a consequence of extreme space-time curvature caused by a concentrated mass. They are not identical structures, but the fact that the size of our observable universe matches the Schwarzschild radius for its total mass is not something anyone predicted. It is not something that falls naturally out of the standard cosmological model. It is a numerical coincidence that happens to align two completely different concepts in a way that makes physicists very, very nervous. Coincidences in physics tend to mean something. When two unrelated quantities turn out to have the same value, it is usually because there is a deeper relationship you have not understood yet. When the charge of the electron is exactly equal in magnitude to the charge of the proton, that is not an accident. It reflects a symmetry in the underlying theory. When the rate of expansion of the universe today happens to sit at the exact value that makes space nearly flat, that is not random chance. It points towards something that happened in the early universe, a period of rapid inflation that smoothed out the geometry. The matching of the observable universe size to the Schwarzschild radius for its mass could be a fluke, or it could be a hint, a clue buried in the structure of space-time, pointing towards something fundamental about the nature of the cosmos that we have been missing. Some physicists have taken this coincidence seriously enough to ask whether the universe we live in might actually be the interior of a black hole. Not metaphorically, literally. Whether the Big Bang, the event we have always thought of as the beginning of time, might instead be the moment our universe crossed an event horizon. Whether every galaxy, every star, every atom in existence might be falling toward a singularity we have not recognized yet because we are looking at it from the inside. Others argue the coincidence is meaningless, a consequence of how we define the observable universe and the particular units we use to measure mass and distance. Change the cosmological parameters slightly and the numbers drift apart. Add in uncertainties about dark energy and the exact matter content of the universe, and the match becomes less impressive. But here is the problem. Even if you dismiss the numerical coincidence as a fluke, you still have to explain why the universe has a horizon at all, why there is a boundary beyond which we cannot see, why information is confined to a finite region of space, why the cosmos, for all its vastness, has edges from our perspective. Black holes and observable universes are the only two structures in physics that share this property. They both have horizons. They both define regions of spacetime from which information cannot escape or cannot reach an observer. One is formed by collapse, the other is a consequence of expansion. But the geometry they produce is uncomfortably similar. And that similarity is not just philosophical. It shows up in the math. The equations that describe the curvature of spacetime inside a black hole and the equations that describe the expanding universe are both solutions to Einstein's field equations. They are both valid descriptions of how spacetime can be shaped by mass and energy. In certain cases, the metrics that describe these two situations can be transformed into one another through a change of coordinates. They are not identical, but they are disturbingly close cousins. Einstein's field equations do not care whether you call something a black hole or a universe. They just describe how spacetime bends in response to whatever mass and energy you put into them. Feed in one set of conditions and you get a collapsing star forming an event horizon. Feed in a different set and you get an expanding cosmos with a particle horizon. The equations treat both as legitimate geometries. So when the size of the observable universe happens to match the Schwarzschild radius of its contents, you are looking at a situation where two different solutions to the same equations are giving you the same answer. That is not something you can wave away easily. The standard cosmological model, the one that has worked beautifully for decades to explain everything from the cosmic microwave background to the large-scale structure of galaxies, does not predict this coincidence. It does not forbid it either. It just does not address it. The model tells you how the universe expands. It tells you how structure forms. It tells you the age and size and composition of the cosmos. But it does not explain why the size of the region you can observe happens to line up with the event horizon size for the mass inside that region. That gap in the explanation is what makes this disturbing. Not because the math is wrong, the math is fine, but because the math is pointing at something and no one can agree on what it is pointing at. If you take the coincidence seriously, you start asking uncomfortable questions. If the observable universe is roughly the size of a black hole with its mass, does that mean we are inside one? If we are inside one, where is the singularity? When is the singularity? Is it in our past, at the Big Bang? Or is it in our future, at the end of time when the universe stops expanding and collapses back in on itself, assuming it ever does? And if the Big Bang was not the beginning of time, but the moment we crossed an event horizon, what was on the other side? What universe did we fall out of? Whose black hole are we living inside? These are not idle speculations. These are questions that follow directly from taking the numbers seriously, and the numbers, whether you like them or not, are sitting there on the page, refusing to go away. The observable universe is 93 billion light-years wide. It contains a certain amount of mass. That mass, if compressed, would form a black hole with an event horizon 93 billion light-years wide. You are sitting inside a structure that is exactly the size it would need to be to trap light, and nobody can tell you for certain whether that is an accident. This is not the first time cosmology has stumbled into uncomfortable territory. 100 years ago, Einstein added a cosmological constant to his equations because he could not accept that the universe might be expanding. He called it his biggest blunder. Decades later, astronomers discovered that not only is the universe expanding, the expansion is speeding up. The cosmological constant came back, rebranded as dark energy, and now it dominates the universe's fate. The thing Einstein tried to throw out turned out to be real. 50 years ago, physicists thought black holes were mathematical curiosities, exotic solutions to Einstein's equations that probably did not exist in nature. Then they found them, thousands of them, including monsters at the centers of galaxies weighing billions of times the mass of the Sun. The things we thought were impossible turned out to be everywhere. Now we have a number, a coincidence. A strange alignment between the size of the universe we can see and the size of the black hole that universe's mass would create. Maybe it means nothing. Maybe it is a fluke of how we measure things, a quirk of perspective with no deeper significance. Or maybe we have been living inside a black hole the entire time, looking out at the walls of our prison, mistaking them for the open sky. And if that is true, then everything we thought we understood about where we are and how we got here needs to be rewritten from the ground up. The equations that describe black holes are the same equations that describe the universe. They were written by the same man decades before anyone realized what they truly meant. And now those equations are whispering something we are not sure we want to hear. The universe does not owe you common sense. Gravity is not a force pulling you toward the ground. Space and time are not separate things. The cosmic stage you assume is fixed and absolute is actually bending, stretching, and warping under every object that exists within it. And the man who figured that out did so by sitting in a chair and thinking very hard about what would happen if you fell off a roof. His name was Albert Einstein, and in 1907, while working as a patent clerk in Switzerland, he had what he would later call the happiest thought of his life. He imagined a man falling freely from the top of a building. During the fall, the man would feel weightless. If he dropped an apple at the same moment, the apple would float next to him, neither rising nor falling relative to his body. For the duration of that fall, the man would experience no gravity at all. Einstein realized in that moment that acceleration and gravity were not just similar, they were indistinguishable. A person in free fall does not feel gravity. A person standing still on the surface of a planet feels the ground accelerating upward into their feet. That sounds like nonsense. The ground is not accelerating. You are standing still. But Einstein was not talking about motion through space. He was talking about motion through space-time, and that distinction rewrote physics. For more than 2 centuries, gravity had been explained by Isaac Newton's law of universal gravitation. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It worked. It predicted the orbits of planets, the trajectories of cannonballs, the tides. Newton's gravity was one of the most successful theories in the history of science, but it had a problem. It did not explain how gravity actually worked. It just described what gravity did. Two objects separated by empty space somehow knew to pull on each other instantaneously across any distance with no mechanism. Newton himself admitted he had no idea how that could be. He called it action at a distance, and he hated it. But the math worked, so everyone moved on. Einstein could not move on. The happiest thought led him down a path that took 8 years to complete. By 1915, he had constructed a new theory of gravity. He called it General Relativity, and it did not just improve on Newton, it replaced him. In Einstein's theory, gravity is not a force at all, it is geometry. Mass and energy do not pull on each other across space. They warp the space around them, and objects move along the curves that warping creates. Picture a trampoline. Lay it flat and place a bowling ball in the center. The fabric dips. Now roll a marble across the trampoline. It will not travel in a straight line. It will curve toward the bowling ball, not because the ball is pulling on it, but because the surface it is rolling on is no longer flat. The marble is following the straightest possible path it can, but that path has been bent by the shape of the trampoline itself. That is gravity. Mass curves space-time. Objects move along those curves. What you experience as the pull of gravity is actually the result of trying to move through a landscape that has been warped out of flatness. The trampoline analogy gets used so often it has become a cliché, and like most analogies, it breaks down if you push it too hard. For one thing, the trampoline bends downward because of Earth's gravity, which means you are using gravity to explain gravity. For another, the analogy only shows the bending of space, but general relativity describes the bending of space-time. Time itself runs at different rates depending on how strong the gravitational field is. Clocks tick slower near a massive object than they do far away. Time is not a constant background against which events unfold. It is part of the fabric, and it bends just like space does. Still, the trampoline gets the essential point across. Space-time is not a rigid stage. It is a dynamic structure that responds to whatever you put into it. And the rules for how it responds are encoded in a set of equations Einstein published in November 1915. They are called the Einstein field equations, and they are some of the most elegant and terrifying objects in theoretical physics. On one side of the equations, you have a mathematical description of the curvature of spacetime. On the other side, you have the distribution of mass and energy. The equations say that these two things are equal. Tell me how much mass and energy is in a region of space, and I can calculate how spacetime curves. Tell me how spacetime is curved, and I can tell you what mass and energy must be there to produce that curvature. Geometry on one side, matter on the other, and they determine each other. John Archibald Wheeler, one of the physicists who spent decades exploring the implications of general relativity, summarized the theory in a single sentence. Spacetime tells matter how to move. Matter tells spacetime how to curve. That is the entire game. Everything else is detail. The equations are not easy. They involve objects called tensors, which are generalizations of vectors that let you describe how things change in curved spaces. Solving them requires advanced mathematics, and in most cases, exact solutions are impossible to find. You have to use approximations, numerical simulations, or very special symmetries to make progress. But when you do solve them, what comes out is a description of the shape of space-time itself, and some of those shapes are deeply strange. One of the first exact solutions was found by Carl Schwarzschild in 1916, just months after Einstein published the field equations. Schwarzschild was a German physicist serving on the Russian front during World War I. While stationed in the trenches, he worked out the geometry of spacetime around a perfectly spherical, non-rotating mass. He sent his solution to Einstein, who was stunned that anyone had found an exact answer so quickly. The Schwarzschild solution describes the spacetime around something like a star or a planet. Far from the object, spacetime is nearly flat, and the predictions match Newton's law almost perfectly. Closer in, the curvature gets stronger. Time slows down, paths bend more sharply, but nothing truly strange happens until you reach a critical radius, a distance from the center where the curvature becomes so extreme that the geometry breaks. That radius is now called the Schwarzschild radius, and it marks the location of the event horizon. If you compress enough mass into a small enough volume so that all of it fits inside its Schwarzschild radius, you create a black hole. The event horizon is not a physical surface, it is a boundary in space-time. Cross it, and the direction toward the center becomes your future, not metaphorically. Literally, the inward direction shifts from being a direction in space to being a direction in time. You cannot avoid moving toward the singularity any more than you can avoid moving toward next Tuesday. The geometry of space-time itself forces you inward. Light tries to escape and fails, not because something is pulling it back, but because every path it could take, every trajectory through space-time leads inward. Outside the event horizon, you can still escape if you move fast enough. You can fire your rockets, fight against the curvature, and climb back out. It takes energy, but it is possible. Inside the event horizon, escape is not difficult, it is meaningless. There is no direction you can point that leads out. The singularity is not in front of you. It is in your future, and your future is the one place you cannot avoid going. This is what general relativity predicts. Einstein himself did not believe black holes could actually form in nature. He thought the equations were telling him something about the limits of the theory, not about real objects that could exist. But the equations did not care what Einstein believed. They described black holes as valid solutions, and it turned out the universe was full of them. The singularity, sitting at the center of a black hole, is the point where the equations stop making sense. The curvature of spacetime becomes infinite. Density becomes infinite. The concept of a smooth geometry breaks down completely. General relativity, which works beautifully everywhere else, fails at the singularity. That does not mean singularities are not real. It means we do not have the right theory to describe what happens there. Most physicists expect that quantum mechanics, which general relativity does not account for, becomes important at those scales. A theory of quantum gravity, if we ever build one, would replace the singularity with something less pathological. But we do not have that theory yet. So the singularity remains, sitting in the equations like a warning sign. The event horizon is different. The event horizon is not a place where the theory breaks. It is a perfectly well-defined surface in space-time. If you fell through an event horizon, you would not notice anything special at the moment you crossed it. You would not hit a wall. You would not feel a discontinuity. Locally, space-time near the horizon is smooth. The problem is not what happens to you. The problem is what happens to the rest of the universe. As you fall toward the horizon, time dilation becomes extreme. Clocks far away from the black hole appear to tick faster and faster. If you could somehow look back as you fell, you would see the outside universe speed up. Stars would age, galaxies would drift. Billions of years of cosmic history would flash by in the final moments before you crossed the horizon. And once you cross, the universe you left behind is gone. Not hidden, not far away. It is in your past, permanently and irreversibly separated from your future by the geometry of space-time. From the perspective of someone watching you fall, the opposite happens. As you approach the horizon, you appear to slow down. Light from your body gets redshifted, stretched to longer and longer wavelengths. You grow dimmer. Time dilation makes every second of your experience take longer and longer from the outside perspective. In principle, you never quite reach the horizon. You asymptotically approach it, fading from view as the light carrying your image weakens and reddens into invisibility. For you, the crossing happens in finite time. For the outside universe, it takes forever. Two observers, two descriptions of the same event, both correct within their own reference frames. That is relativity. General relativity does not just predict black holes, it also describes the large-scale structure of the universe. In 1917, just a year after Schwarzschild found his solution, Einstein applied his field equations to the cosmos as a whole. He made two simplifying assumptions. First, that the universe is homogeneous, meaning it looks the same at every point. Second, that it is isotropic, meaning it looks the same in every direction. These assumptions are not exact, but on the largest scales, they are surprisingly good. Galaxies are not distributed uniformly, but average over hundreds of millions of light-years, and the clumps smooth out. The universe, statistically speaking, has no preferred location and no preferred direction. Einstein plugged those assumptions into his field equations and found something he did not expect. The equations told him the universe could not be static. It had to be either expanding or contracting. The geometry of space-time on cosmic scales is dynamic. It evolves. That conclusion made Einstein deeply uncomfortable. In 1917, the idea of an expanding universe was not just unexpected, it was philosophically unacceptable to most scientists, including Einstein. The cosmos was supposed to be eternal and unchanging, a vast fixed arena in which events played out but which itself did not evolve. So Einstein did what seemed reasonable at the time. He modified his equations. He added a new term, a constant that represented a kind of intrinsic energy in empty space itself. This term, the cosmological constant, acted as a repulsive force that could exactly balance the attractive pull of gravity and hold the universe static. The math worked. The static universe was restored, and Einstein moved on. 12 years later, Edwin Hubble published observations showing that distant galaxies are receding from us, and the farther away they are, the faster they are moving. The universe was expanding, exactly as the original, unmodified field equations had predicted. Einstein reportedly called the cosmological constant his biggest blunder. He had been handed evidence of one of the most profound discoveries in the history of science, a universe that changes over time, and he had talked himself out of believing it because it clashed with his intuition. The cosmological constant came back, by the way. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Something is pushing space apart, and that something behaves almost exactly like the term Einstein added and then removed. We call it dark energy now, and it dominates the universe's future. The biggest blunder turned out to be real. Einstein was right the first time, for the wrong reasons. General relativity connects black holes and cosmology in ways that are not immediately obvious. Both involve extreme curvatures of space-time. Both are described by the same equations. A black hole curves space-time so strongly that it traps light within a region. The universe as a whole has a geometry that can trap information within a horizon, the boundary of the observable universe beyond which we cannot see. The math describing these two situations is not identical, but it rhymes. Einstein's field equations allow for many different solutions, many different possible shapes for spacetime. The Schwarzschild solution describes the space around a spherical mass. The Kerr solution, found in 1963, describes a rotating black hole. The Friedmann equations, derived in the 1920s, describe an expanding or contracting universe. All of these are valid geometries. All of them solve the same underlying equations. The universe does not care which one it is, it just follows the math. And here is where things get unsettling. If the equations treat black holes and universes as different solutions to the same problem, is it possible that what we call the universe might actually be a black hole viewed from the inside? That the Big Bang was not the beginning of time, but the moment we crossed an event horizon? That every galaxy we see is falling toward a singularity we have not recognized because the geometry looks different when you are inside it? These are not mainstream ideas. Most cosmologists would tell you the observable universe and a black hole are distinct structures with distinct properties, and that the numerical coincidence between their sizes is just that, a coincidence. But the fact that the question can even be asked, that the math leaves room for it, is a consequence of how general relativity works. It describes geometry. It does not care about labels. It does not privilege one solution over another. Feed it the right initial conditions, and it will give you a black hole. Feed it different conditions, and it will give you a universe. Ask it whether the two might somehow be the same thing viewed from different perspectives, and it does not say no. Space-time is not a backdrop. It is not a container that holds the universe. It is the universe. Matter and energy are not things that exist in space. They are patterns in the geometry of space-time itself, ripples and curves and twists in the fabric. General relativity tells you that geometry is dynamic, that it responds to what you put into it, and that the shapes it can take are far stranger than anything our everyday experience prepares us for. Black holes are one of those shapes. The universe is another. And the equations that describe both were written by the same man a century ago, in a theory that has passed every experimental test we have ever thrown at it. Einstein's ghost is still in the machine, quietly shaping the questions we are only now beginning to know how to ask. In 1922, a Russian mathematician named Alexander Friedmann did something that should have changed cosmology overnight. He took Einstein's field equations, the same equations that predicted black holes and bent spacetime, and he asked a simple question. What happens if you apply these equations not to a star or a planet, but to the entire universe at once? Einstein had already tried this. He had applied his equations to the cosmos in 1917 and immediately ran into a problem. The equations told him the universe could not sit still. It had to be either expanding or contracting. Einstein, who believed the universe was eternal and static, added the cosmological constant to hold everything in place. He forced the math to give him the answer he wanted. Friedmann did not force anything. He just solved the equations, and what came out was a universe that moved, a universe that evolved, a universe whose size changed with time, growing larger or shrinking smaller, depending on what you put into it. He published his solution in a German physics journal, and almost nobody paid attention. Einstein himself wrote a response, dismissing Friedmann's work as mathematically incorrect. Friedmann wrote back, politely, showing that the math was fine. Einstein published a retraction, but the damage was done. The idea of an expanding universe was too strange, too far outside the acceptable framework. Friedmann's equations were filed away as a mathematical curiosity. Then Edwin Hubble pointed a telescope at distant galaxies and measured their motion. They were receding. The farther away a galaxy was, the faster it was moving. Space itself was expanding, exactly as Friedmann's equations predicted. By the time the astronomical community realized Friedmann had been right all along, he was already dead. He died in 1925 at the age of 37 from typhoid fever. He never saw his equations become the foundation of modern cosmology. Today, those equations are called the Friedmann equations, and they are the blueprint for how we understand the universe. If you want to know how old the universe is, you use the Friedmann equations. If you want to know how fast it is expanding, you use the Friedmann equations. If you want to predict whether the universe will keep expanding forever or eventually collapse back in on itself, you solve the Friedmann equations and see what they tell you. Every major cosmological model for the last century has been built on top of the framework Friedmann laid out in a few pages of dense mathematics in 1922. The equations themselves look deceptively simple when you strip away the notation. There are two of them. The first one relates the expansion rate of the universe to its energy content. The second one tells you how that expansion rate changes over time. Together, they describe the entire life story of the cosmos, from the Big Bang to whatever end awaits it. Let me walk you through what they actually say, because this is where things start to get strange. The first Friedmann equation is the one that gets called the most important equation in cosmology. On the left side, you have the square of the Hubble parameter. The Hubble parameter is just the expansion rate of the universe at any given moment. Right now, that rate is about 70 kilometers per second per megaparsec, though, as we talked about earlier, nobody can agree on the exact number. The Hubble parameter changes over time. It was much higher in the early universe when everything was packed closer together. It will be lower in the future as the expansion continues. The Friedmann equations let you calculate how it evolves. On the right side of the equation, you have three terms. The first term is 8 pi times the gravitational constant times the energy density, all divided by 3. Energy density just means how much stuff, matter, and energy is packed into each cubic meter of space. More stuff means stronger gravity, which affects how the universe expands. The second term involves the curvature of space. Space can be flat, like a sheet of paper. It can be positively curved, like the surface of a sphere. Or it can be negatively curved, like a saddle. That curvature shows up in the equations as a number called k. If k is 0, space is flat. If k is positive, space curves back on itself. If k is negative, space curves outward. The third term is the cosmological constant, the thing Einstein added and then regretted. Except it turns out it is real, and we now call it dark energy. Put all three terms together and you get the expansion rate. Tell me how much matter is in the universe, how much dark energy, and what the curvature is, and I can calculate how fast space is expanding right now. That is what the first Friedmann equation does. It connects the geometry of space-time to the stuff inside it. The second Friedmann equation is about acceleration. The first equation tells you how fast the universe is expanding. The second tells you whether that expansion is speeding up or slowing down. On the left side, you have the second derivative of the scale factor, a mathematical way of describing how the expansion rate itself is changing. On the right side, you have terms involving the energy density and the pressure of whatever fills the universe. Pressure, in this context, does not mean the kind of pressure you feel when you squeeze a balloon. It is a thermodynamic quantity that describes how energy and momentum are distributed in space. Normal matter has positive pressure. Radiation has positive pressure. Dark energy has negative pressure. That negative pressure is what makes dark energy so weird. Positive pressure slows down expansion. Negative pressure speeds it up. That is why the discovery of dark energy was so shocking. The universe is not just expanding, the expansion is accelerating. Something is pushing space apart, and that something behaves like it has negative pressure. The second Friedmann equation captures that. It tells you that if the universe is dominated by matter, the expansion slows down over time. Gravity pulls everything together, fighting against the outward motion. If the universe is dominated by dark energy, the expansion speeds up. The negative pressure overwhelms gravity and drives everything apart faster and faster. Right now, the universe is in the process of transitioning from a matter-dominated era to a dark energy-dominated era. The expansion rate is increasing. Billions of years from now, if dark energy stays constant, galaxies will be receding from us so fast that light from new galaxies will never reach us. The observable universe will shrink, not because space is collapsing, but because the things we can see will race beyond our horizon. This is the machinery that runs the cosmos. These two equations, derived from Einstein's General Relativity, under the assumption that the universe is smooth and uniform on large scales. That assumption is called the cosmological principle. It says the universe has no center and no edge. Every point in space is equivalent to every other point. Every direction looks the same. Obviously, that is not true on small scales. Galaxies cluster together. There are voids where almost nothing exists, but average over hundreds of millions of light years and the clumps smooth out. The universe becomes homogeneous and isotropic, the technical terms for smooth and uniform. Those assumptions let you simplify Einstein's field equations enormously. Instead of dealing with every local variation in density and curvature, you can treat the universe as a single evolving entity described by a handful of parameters. The scale factor is one of those parameters. It is usually written as r, and it describes the relative size of the universe as a function of time. If r doubles, every distance in the universe doubles. Galaxies move farther apart. Light traveling through space gets stretched. The scale factor does not have units of length. It is just a number that tracks how much the universe has grown or shrunk. By convention, we set r equal to 1 today, so any time in the past corresponds to an r less than 1, and any time in the future corresponds to an r greater than 1. At the moment of the Big Bang, r was 0. All distances were 0. The universe had no size. That is the singularity, the point where the math breaks down and the equations stop making sense. The Hubble parameter is the time derivative of the scale factor divided by the scale factor itself. It measures how fast r is changing. If the universe is expanding, the Hubble parameter is positive. If it were contracting, the Hubble parameter would be negative. Right now, the Hubble parameter is positive and has been for the entire history of the universe as far as we can tell. The expansion has never reversed. That might change in the far future, depending on what dark energy does, but for now, space is getting bigger. The energy density is the sum of contributions from everything in the universe, matter, both ordinary and dark. Radiation, which includes photons and other massless particles. Dark energy. Each component contributes to the total density, and each component affects the expansion in a different way. Matter dilutes as the universe expands. If you double the size of the universe, the same amount of matter is now spread over 8 times the volume, so the density drops by a factor of 8. Radiation dilutes even faster, because, in addition to being spread over more volume, each photon loses energy as its wavelength stretches. Double the size of the universe, and radiation density drops by a factor of 16. Dark energy does not dilute at all. It has a constant energy density, no matter how much the universe expands. That is what makes it so dominant in the long run. Matter and radiation fade away. Dark energy stays the same. There is a special value of the total energy density called the critical density. If the universe has exactly the critical density, space is flat. The curvature term in the Friedmann equation goes to zero. The expansion continues forever, but it slows down asymptotically, approaching zero speed in the infinite future. If the density is higher than critical, space curves positively, like a sphere. The universe is closed. Gravity is strong enough to eventually halt the expansion and pull everything back together in a big crunch. If the density is lower than critical, space curves negatively, like a saddle. The universe is open. The expansion continues forever and never slows to a stop. Observations tell us the universe is almost exactly at critical density. Space is flat, or so close to flat that we cannot measure the difference. That is another coincidence that bothers physicists. Why should the universe be balanced so precisely on the edge between open and closed? The answer, most likely, is inflation. A period of exponential expansion in the first fraction of a second after the Big Bang that stretched space so flat that any curvature became undetectable. Inflation solved the flatness problem, but it also raised new questions about what caused inflation and how it ended. Those questions are still open. The Friedmann equations do not care about any of that. They just take the density and the curvature and the cosmological constant and spit out the expansion rate. They are completely general. You can plug in whatever values you want and see what kind of universe you get. If you set the cosmological constant to zero and assume the universe is dominated by matter, you get a universe that expands but slows down over time. Eventually, billions of years from now, the expansion grinds to a halt and reverses. Everything collapses back into a singularity. If you include dark energy, the universe expands forever. The galaxies drift apart, stars burn out, black holes evaporate. The cosmos ends not in a crunch, but in a slow fade to cold, empty darkness. Different initial conditions give you different universes. The Friedmann equations describe all of them. And here is where the parallel to black holes starts to show up in the math, because the equations that describe the expanding universe and the equations that describe the interior of a black hole are disturbingly similar. Inside a black hole, space and time swap roles. The inward direction becomes a direction in time, not space. You cannot avoid moving toward the singularity any more than you can avoid moving toward the future. The geometry inside the event horizon is described by the same Einstein field equations that describe the universe, just with different boundary conditions. When you solve those equations for the interior of a black hole, you get a metric that looks a lot like the metric for an expanding universe. In both cases, you have a scale factor that changes with time. In both cases, you have a singularity. In a black hole, the singularity is in your future. It is the place where the curvature becomes infinite and the equations break. In the expanding universe, the singularity is in your past. It is the Big Bang, the moment when the scale factor was zero and everything was compressed into a point. But mathematically, the structure is the same. A region of spacetime bounded by a singularity, described by a metric that evolves according to Einstein's equations. There is a specific solution to the Friedmann equations that makes this parallel even sharper. It is called the flat, matter-dominated universe. Set the cosmological constant to zero. Set the curvature to zero. Assume the universe is filled with matter and nothing else. Solve the equations and you get a scale factor that grows as time to the 2/3 power. The expansion slows down over time, but it never stops. The universe grows without bound, but the rate of growth decreases. Now take the metric that describes the interior of a Schwarzschild black hole and rewrite it in a particular set of coordinates. In those coordinates, the geometry inside the black hole looks almost identical to the geometry of a flat, matter-dominated universe. The roles of space and time are swapped, but the mathematical form of the metric is the same. The singularity at the center of the black hole plays the same role as the Big Bang singularity in the cosmological model. The event horizon plays the same role as the particle horizon that bounds the observable universe. This is not a loose analogy. It is a direct mathematical correspondence. The equations are the same. The geometries are related by a coordinate transformation. If you were a mathematician handed both solutions without being told which one described a black hole and which one described the universe, you might have trouble telling them apart. Does that mean the universe is a black hole? Not necessarily. The correspondence is exact only for very specific choices of parameters. Real black holes rotate. Real black holes are not filled with a smooth distribution of matter. The real universe is not perfectly flat and not perfectly matter-dominated. Dark energy changes everything. But the fact that the equations even allow for this kind of overlap is unsettling. It means the boundary between what we call a universe and what we call a black hole is thinner than you might expect. General relativity treats both as valid solutions to the same problem. You give it initial conditions, and it tells you how space-time evolves. Feed it the conditions inside an event horizon, and you get a black hole interior. Feed it the conditions of a homogeneous, isotropic cosmos, and you get the Friedmann equations. The math does not privilege one over the other. They are both just shapes space-time can take. And if the observable universe has a size that matches the Schwarzschild radius for its mass, then you are looking at a situation where the numbers describing our universe happen to line up with the numbers describing a black hole. The equations that govern how our universe expands are the same equations in a different guise that govern how space-time behaves inside an event horizon. That does not prove we are inside a black hole, but it does mean the possibility is not ruled out by the math. The framework allows it. Friedmann never knew any of this. He solved the equations, published the results, and died before anyone took him seriously. He never lived to see Hubble confirm that the universe expands. He never saw the cosmic microwave background discovered, the leftover radiation from the Big Bang that proved the universe had a hot, dense beginning. He never saw dark energy or dark matter or the precision measurements that let us determine the age of the universe to within a few tens of millions of years. All of that came later, built on the foundation he laid in 1922. The Friedmann equations are cosmology's most important equation, not because they answer every question, but because they frame the questions in a way that lets you calculate answers. They connect the expansion of the universe to its contents. They let you run time forward or backward and see what happens. They are the reason we can say the universe is 13.8 billion years old with confidence. They are the reason we know dark energy exists. They are the reason we can predict the future of the cosmos. And they are also, whether by coincidence or by something deeper, the reason we can draw a mathematical line between the universe we live in and the interior of a black hole. The same equations describe both. The same geometry underlies both. And if you take the parameters that describe our universe and plug them into the formula for a black hole's event horizon, you get a number that matches the size of the observable universe. Friedmann gave us the tools to calculate the fate of the cosmos. He also, without meaning to, gave us the tools to ask whether the cosmos might be something other than what we assumed. Whether the Big Bang might not be a beginning, but a crossing. Whether the expansion we measure might not be the universe growing into empty space, but space itself behaving the way it does inside a horizon. The math leaves the door open, and the numbers quietly keep pointing at that door. The Hubble constant is a number that refuses to sit still. For nearly a century, it has been the single most important measurement in cosmology, the number that tells you how fast the universe is expanding right now. And for nearly that entire century, nobody has been able to agree on what it actually is. The constant is named after Edwin Hubble, the astronomer who in 1929 published a paper showing that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it is receding. That relationship, the one between distance and recession speed, is what we now call Hubble's law. The proportionality constant in that relationship, the number that connects how far something is to how fast it is moving away, is the Hubble constant. It is usually written as h0, and it is measured in units of kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So if the Hubble constant is 70 kilometers per second per megaparsec, that means for every megaparsec of distance you look outward, galaxies are moving away from you 70 kilometers per second faster. Hubble himself calculated a value of about 500 kilometers per second per megaparsec. That number was wildly wrong. It made the universe appear younger than the Earth, which was awkward. The problem was that Hubble had miscalibrated his distance measurements. He was using a type of variable star called a Cepheid to estimate how far away galaxies were, but he had mistaken one class of Cepheid for another. The two classes have different intrinsic brightnesses, and the error threw off every distance in his ladder. Fix the calibration and the Hubble constant drops. For decades after Hubble's original measurement, two camps of astronomers fought over whether the true value was closer to 50 or closer to 100. The disagreement was not minor. A factor of 2 difference in the Hubble constant translates to a factor of 2 difference in the age of the universe. If the constant is 100, the universe is younger. If it is 50, the universe is older. You cannot build a coherent cosmology if you do not know how old the thing you are studying is. By the late 1990s and early 2000s, the measurements had converged. Most teams were reporting values around 70, give or take a few. The war was over. The Hubble constant had been pinned down. Textbooks printed the number with confidence. Students memorized it. The universe, it seemed, was expanding at a rate everyone could agree on. Then the measurements got better, and the agreement fell apart. There are 2 main ways to measure the Hubble constant, and they give different answers. The first method looks at the universe today. It uses a technique called the cosmic distance ladder, a step-by-step process of measuring distances to progressively farther objects. You start with something nearby whose distance you can measure directly, like a star whose parallax you can observe as Earth orbits the Sun. Then you find a type of object whose brightness you can calibrate using those nearby examples. Cepheid variable stars are a favorite because their brightness fluctuates in a way that is directly tied to how luminous they actually are. Measure the period of the fluctuation and you know how bright the star truly is. Compare that to how bright it looks from Earth and you can calculate the distance. Once you have distances to nearby Cepheids, you can use them to calibrate the brightness of objects in the same galaxies, like Type 1a supernovae. These supernovae are useful because they all explode with roughly the same peak brightness. Once you have calibrated them using Cepheids in nearby galaxies, you can spot them in galaxies hundreds of millions of light years away and calculate those distances. Combine the distances with measurements of how fast those galaxies are receding, and you get the Hubble constant. A team led by Adam Rees at Johns Hopkins University has been refining this method for years. Their project is called SH0ES, which stands for supernova H0 for the equation of state. They have used the Hubble Space Telescope and now the James Webb Space Telescope to measure distances to galaxies across a huge range of the cosmos. Their most recent results, published in 2024, give a Hubble constant of about 73 kilometers per second per megaparsec. The uncertainty is small. The measurements are precise. The method has been checked and rechecked, and 73 is the number they keep getting. The second method looks at the early universe. Instead of building a distance ladder from nearby objects outward, it uses a snapshot of the cosmos when it was only 380,000 years old. That snapshot is the cosmic microwave background, the faint glow of radiation left over from the moment the universe cooled enough for atoms to form. The European Space Agency's Planck satellite spent years mapping this radiation with extraordinary precision. From that map, physicists extracted the conditions of the early universe: the density of matter, the density of radiation, the curvature of space. They plugged those conditions into the standard cosmological model and ran the equations forward 14 billion years to predict how fast the universe should be expanding today. The answer they got was 67.7 kilometers per second per megaparsec, not 73. 67.7. The two methods disagree by about 8%. That might not sound like much, but in a field where measurements are often precise to within 1%, an 8% gap is enormous. It is the difference between a universe that is about 14 billion years old and one that could be more than a billion years younger. It changes the timeline for when the first stars formed, when galaxies assembled, when the conditions for planets and life became possible. And nobody knows which number is right, or whether both are wrong. This disagreement is called the Hubble tension, and it has been the subject of hundreds of papers and countless conferences. Some researchers think the distance ladder measurements are being thrown off by something subtle, an unaccounted source of error in the calibration of Cepheids or supernovae. Others think the early universe measurements are missing some piece of physics, some effect that was important in the first few 100,000 years that we have not included in the models. A few think the standard cosmological model itself is wrong, that the equations we have been using for decades are missing something fundamental. The tension has not gone away. If anything, it has gotten worse as the measurements have gotten more precise. The James Webb Space Telescope was supposed to settle this. Its sharper vision and greater sensitivity were expected to clean up any lingering uncertainties in the distance ladder. When Webb turned its instruments toward the same galaxies Hubble had observed, many in the field expected the 73 to drop and the tension to relax. That is not what happened. Webb confirmed Hubble's measurements almost exactly. The distance is held. The Hubble constant stayed at 73. In early 2024, the SH0ES team published a paper announcing they had now used Webb to span the full range of Hubble's observations, measuring more than 1,000 Cepheid variables across 5 galaxies hosting 8 supernovae. The conclusion was clear. Measurement error was not the problem. Something else was going on. Adam Rees, who shared the Nobel Prize in Physics for the discovery that the universe's expansion is accelerating, put it bluntly: with measurement errors ruled out, what remains is the real and exciting possibility that we have misunderstood the universe. That quote has been repeated in dozens of articles and presentations because it captures the stakes. This is not a minor calibration issue. This is a crack in the foundation. Now here is where things get strange, and this is the part that does not get talked about much outside certain corners of theoretical physics. The Hubble constant is not just a number that tells you how fast galaxies are moving apart. It is a number that describes the geometry of space-time itself. In the Friedmann equations, the ones that govern how the universe evolves, the Hubble constant shows up as the time derivative of the scale factor divided by the scale factor. That is a fancy way of saying it measures how quickly the size of the universe is changing relative to its current size. It is a rate of change for space-time geometry. And that rate of change, it turns out, has a parallel in black hole physics. Inside a black hole, the geometry of space-time is described by a set of coordinates that map out how distances and times are measured. One of those coordinate systems, called Painlev-Gullstrand coordinates, makes the interior of a black hole look a lot like an expanding universe. In these coordinates, space inside the event horizon is falling inward toward the singularity. But from the perspective of someone inside, it looks like space is expanding. The singularity is not a place in space, it is a moment in time, somewhere in your future. And the rate at which space appears to expand in these coordinates is governed by a parameter that plays the same role as the Hubble constant in cosmology. The math here is dense, but the idea is simple. If you are inside a black hole and you do not know it, the geometry around you would look like an expanding universe. Space would appear to be growing, distant objects would appear to be receding, and the rate of that expansion would be set by the mass of the black hole and the radius of the event horizon. You could measure that rate, call it the Hubble constant, and use it to build a cosmology. You would have no idea you were inside a black hole unless you knew to look for it in the numbers. Now take the value of the Hubble constant that the Planck satellite gives you. 67.7 kilometers per second per megaparsec. Run that number through the equations for an interior Schwarzschild solution, the simplest kind of black hole geometry. What you find is that a universe expanding at that rate has a geometry that matches, almost exactly, the interior of a black hole with a mass equal to the total mass of the observable universe. The expansion rate we measure is consistent with what you would observe if you were inside an event horizon, falling toward a singularity, watching space stretch as you fall. This is not a loose analogy, this is a direct mathematical result. The specific value of the Hubble constant that Planck measured, when interpreted through the framework of general relativity, gives you a geometry that is indistinguishable from the interior of a black hole. The rate of expansion, the curvature of space, the evolution of the scale factor, all of it lines up. If you were handed the numbers without being told whether they described a universe or a black hole interior, you would have a hard time telling them apart. The distance ladder measurements, the ones that give you 73 instead of 67, complicate this picture. If the true Hubble constant is 73, the geometry shifts slightly. The correspondence is not as clean. That could mean the black hole interpretation is wrong, or it could mean the 73 is picking up something local, some effect that is not representative of the universe as a whole. The Hubble tension, in this view, might not be a problem with the measurements. It might be a clue that we are measuring two different things. The distance ladder measures expansion in the nearby universe within a few billion light-years. The cosmic microwave background measures expansion on the scale of the entire observable universe. If those two scales are governed by different geometries, you would expect the numbers to disagree. Here is another way to think about it. The Hubble constant is usually interpreted as the rate at which the universe is expanding outward, as if there were some center we are all moving away from. But general relativity tells you there is no center. Every point in space sees every other point receding. The expansion is not happening in space, it is happening to space. Space itself is growing, and that growth carries galaxies along with it. But what if the expansion is not outward at all? What if it is inward? What if the geometry we are living in is the interior of an event horizon, and what we call expansion is actually the inward curvature of space-time as it falls toward a singularity? From the inside, those two situations would look identical. You would see distant galaxies moving away. You would measure redshifts. You would calculate a Hubble constant. And you would have no way to tell, just from the expansion rate, whether you were in an expanding cosmos or inside a black hole. The singularity in this picture is not behind us at the Big Bang. It is ahead of us in the future. The Big Bang is not the moment everything exploded outward from a point. It is the moment we crossed the event horizon, the moment we fell in. And everything we have observed since then, the cooling of the universe, the formation of stars and galaxies, the expansion of space, all of it is just the interior geometry playing out as we fall toward the singularity at the end of time. This interpretation is not mainstream. Most cosmologists would tell you it is speculative, that the standard model explains the data just fine without invoking black holes. And they are right that the standard model works. It predicts the cosmic microwave background. It predicts the abundances of light elements like hydrogen and helium. It predicts the large-scale structure of galaxies. The model has passed every test we have thrown at it for decades. But the model does not explain the Hubble tension. It does not explain why the size of the observable universe matches the Schwarzschild radius for its mass. It does not explain why the expansion rate we measure happens to be the exact value you would expect inside a black hole. The tension in the Hubble constant is real. The numbers do not agree, and every attempt to reconcile them has failed. The measurements keep getting more precise, and the gap stays the same or gets wider. At a conference in 2019, Adam Rees asked David Gross, a Nobel laureate in particle physics, whether the field should start calling this a problem. Gross told him they should call it a crisis. That word has stuck. The Hubble tension is now routinely described as a crisis in cosmology, a fundamental disagreement about the most basic property of the universe that refuses to go away. One possibility that keeps surfacing is called early dark energy. The idea is that in the first few 100,000 years after the Big Bang, there was a burst of extra expansion driven by a field that has since decayed. If something like that happened, it would change the conditions in the early universe just enough to shift the Planck prediction upward, closer to 73, without breaking everything else the standard model gets right. Early dark energy is not confirmed. It is not even widely accepted. But it is one of the few ideas that could solve the Hubble tension without tearing down the entire framework of cosmology. The alternative is that the framework is wrong, that the equations we use to describe the universe, the Friedmann equations that have worked so well for a century, are missing something. Not a small correction, something fundamental. A piece of geometry or a piece of physics that changes the game entirely. Here is what makes the black hole interpretation so unsettling. It does not require new physics. It does not require modifying the equations. It just requires looking at the same equations from a different perspective. General relativity allows for both an expanding universe and the interior of a black hole. They are both valid solutions. And the math that describes one can, under the right conditions, describe the other. If the Hubble constant we measure is the rate at which space is falling inward rather than expanding outward, you do not need to invent new fields or new forces. You just need to accept that the geometry you are living in might not be what you thought it was. The expansion of the universe has been observed since Hubble's original measurements in 1929. Galaxies are moving away from us in every direction. The farther away they are, the faster they move. That pattern has been confirmed over and over with better telescopes, better detectors, better methods. The redshift of distant galaxies, the stretching of light as it travels through expanding space, is one of the most robust observations in all of astronomy. Nobody disputes that the universe is expanding. The question is what that expansion means. If you are inside a black hole, you would also see everything around you receding. The geometry inside an event horizon forces everything to move inward, toward the singularity. But from your perspective, it does not look like you are falling. It looks like space is growing. Distant objects appear to move away. Light gets redshifted. The effect is the same. The interpretation is different. The Hubble constant is the key to telling these two pictures apart, if they can be told apart at all. If the value we measure matches the interior geometry of a black hole, that is evidence, not proof, but evidence that we might be inside one. If the value is different, if it breaks the correspondence, then the black hole interpretation does not hold. Right now, the Planck value of 67.7 fits. The distance ladder value of 73 does not, at least not as cleanly. The tension between those two numbers is not just a measurement problem. It might be a signal that we are trying to fit a single interpretation onto a geometry that does not match our assumptions. There is another piece of this that matters. The Hubble constant is not constant. It changes over time. In the early universe, when everything was packed closer together, the expansion rate was much higher. As the universe ages and matter spreads out, the Hubble parameter decreases. Right now, it is about 70, give or take. In a few billion years, as dark energy takes over and the expansion accelerates, the Hubble parameter will start increasing again. The number we measure today is just a snapshot of where we are in the universe's history. Inside a black hole, the equivalent parameter also changes with time. As you fall deeper into the interior, closer to the singularity, the geometry shifts. The rate at which space appears to expand depends on where you are in your journey toward the singularity. If we are inside a black hole, the Hubble constant we measure today would tell us how far we have fallen, how close we are to the end. And the fact that the number we measure happens to match the geometry of a black hole interior at this particular moment is either the most extraordinary coincidence in physics or a clue that the entire framework needs to be reconsidered. The James Webb Space Telescope has made the Hubble tension worse, not better. It confirmed the distance ladder measurements with higher precision than ever before. It ruled out the most popular explanations for why the numbers might disagree. It showed that the 73 is real, and so is the 67.7, and they both cannot be right unless something fundamental is missing. That missing piece might be early dark energy. It might be a modification to general relativity. It might be a misunderstanding of how we measure distances or how we interpret the cosmic microwave background. Or it might be that the universe we are living in is not what we think it is. The numbers keep pointing at the same conclusion. The size of the observable universe matches the Schwarzschild radius for its mass. The expansion rate we measure matches the interior geometry of a black hole. The singularity we think is in our past could just as easily be in our future, and the Hubble constant, the number that has defined cosmology for a century, might not be telling us how fast the universe is growing. It might be telling us how fast we are falling. The math leaves the door open. The observations refuse to close it. And the tension, the crisis, the gap between what we measure and what we expect sits there in the data, waiting for someone to explain it. Edwin Hubble showed us the universe is expanding. He had no idea. He might have been showing us something else entirely. The standard Big Bang model is cosmology's origin story, and for the better part of a century, it has held up under scrutiny. It says the universe began about 13.8 billion years ago in a state of unimaginable heat and density, not a state located somewhere in space, a state that was space, or rather, a state before space as we know it even existed. Every point in the universe today, every galaxy, every atom, every coordinate you could name, was compressed into a volume so small that our equations break down trying to describe it. This initial moment is called the singularity, and it marks the boundary where physics stops making sense. Time itself, in the standard model, begins at the singularity. There is no before. Asking what happened before the Big Bang is like asking what is north of the North Pole. The question does not pass. Time is a coordinate that only exists after the singularity. Before that, the concept has no meaning. From that initial state, the universe expanded. Not into empty space, because there was no space outside the universe to expand into. Space itself expanded, carrying matter and energy along with it. In the first fraction of a second, something extraordinary happened. A period called inflation, where the universe grew exponentially, doubling in size over and over again in an interval so short that no clock we could build would register it. Inflation smoothed out the early universe, stretching any irregularities flat and setting the stage for everything that came after. When inflation ended, the energy driving it decayed into particles. The universe was filled with a hot, dense soup of fundamental particles, radiation and energy. As space continued to expand, the temperature dropped. Particles combined to form protons and neutrons. Those combined to form the first atomic nuclei. Hundreds of thousands of years later, the universe cooled enough for electrons to bind to nuclei, forming neutral atoms. At that moment, light could finally travel freely through space. The universe went from opaque to transparent. That light, stretched by billions of years of expansion, is what we now detect as the cosmic microwave background. Over the next few 100 million years, gravity pulled matter together into clumps. The first stars ignited, galaxies formed, stars exploded, seeding space with heavy elements. Planets coalesced from the debris. Life appeared, at least once, and probably many more times, scattered across the cosmos. That is the story, from a singularity to stars to you. It explains the expansion we observe. It explains the abundances of hydrogen and helium. It explains the cosmic microwave background. It explains the large-scale structure of galaxies. The model works. Every major prediction it has made has been confirmed by observation. But the model has a problem it cannot shake, and that problem sits right at the beginning, the singularity. The point where density becomes infinite, temperature becomes infinite, and the equations that describe everything else fail completely. General relativity, the theory that gave us the Big Bang model in the first place, tells you that if you run the expansion backward, you eventually reach a moment where the universe had zero size. Every distance goes to zero. Every density goes to infinity. The curvature of spacetime becomes infinite, and at that point, general relativity shrugs and says it can no longer describe what happens. The singularity is not a prediction in the sense of telling you what actually occurred. It is a flag that says the theory has reached its limit. Something is missing. Some piece of physics that general relativity does not include becomes important at those scales. Most physicists think that piece is quantum mechanics. Gravity is the only force we have not successfully merged with quantum theory. We have quantum electrodynamics for electromagnetism. We have quantum chromodynamics for the strong nuclear force. We have electroweak theory for the weak force. But quantum gravity remains out of reach. And until we have it, the singularity at the beginning of the universe remains a black box we cannot open. Here is where things get strange, because there is another place in physics where general relativity predicts a singularity, inside a black hole. At the center of every black hole, hidden behind an event horizon, sits a point where space-time curvature becomes infinite and the equations break. The singularity at the heart of a black hole and the singularity at the beginning of the universe are described by the same mathematics. They are both places where general relativity stops working. They are both boundaries where something new, something quantum, needs to take over. And they are both associated with extreme conditions, infinite density, infinite curvature. Conditions so far removed from everyday experience that our intuition provides no guidance. So here is the question nobody likes to ask out loud. What if the Big Bang was not the beginning of the universe, but the moment we crossed an event horizon? What if the singularity we think is in our past, the moment everything started, is actually the same kind of singularity that sits at the center of a black hole? What if the universe we live in is not expanding outward from a creation event, but falling inward through the geometry of a black hole interior, and the Big Bang was not an explosion but an entrance? This is not a new idea. Versions of it have been floating around in the theoretical physics literature for decades, usually under names like black hole cosmology or Schwarzschild cosmology. It has never gained mainstream acceptance because the standard Big Bang model works so well, and because the idea of reinterpreting the Big Bang as an event horizon crossing introduces complications that are hard to test. But the mathematics allows it. General relativity does not forbid it. And the more precisely we measure the universe, the harder it becomes to dismiss the parallels between the two situations. Start with the initial conditions. The Big Bang model says the universe began in a state of infinite density, compressed into zero volume. That is exactly what you get at the singularity inside a black hole. When a massive star collapses and forms a black hole, all of its mass gets compressed into a point at the center. The density at that point is infinite. The volume is zero. The space-time curvature is infinite. The equations break. If you were somehow inside a black hole, falling toward the singularity, you would encounter those same conditions. The closer you got, the more extreme the curvature would become, until you reached a point where the theory could no longer describe what happens. That point, inside a black hole, is called the singularity. The point at the beginning of the universe, in the Big Bang model, is also called the singularity. They have the same name because they have the same mathematical structure. Now add time to the picture. In normal space, outside a black hole, time is time and space is space. You can move forward or backward in space, but you can only move forward in time. You can turn around and walk back the way you came, but you cannot reverse the flow of time and move into the past. Time has a direction, and that direction is fixed. Inside a black hole, that changes. Once you cross the event horizon, the roles of space and time swap. The direction toward the singularity, the inward direction, stops being a direction in space. It becomes a direction in time. You cannot avoid moving toward the singularity any more than you can avoid moving toward next Tuesday. It is not that something is pulling you in. It is that every possible path through space-time, every trajectory you could follow, points inward. The singularity is not a place you are falling toward. It is a moment in your future, and your future is the one thing you cannot avoid. This inversion, this swapping of space and time inside an event horizon, is one of the strangest predictions of general relativity, and it has a direct parallel in cosmology. In the standard Big Bang model, the singularity is not a place, it is a moment. It is the beginning of time. Every trajectory through space-time, if you run it backward, points toward that moment. You cannot go around it. You cannot avoid it. It is in the past of every point in the universe, the same way the singularity inside a black hole is in the future of every point inside the event horizon. The geometry is the same. The roles of space and time are inverted in both cases. The only difference is whether the singularity is behind you or ahead of you. If the Big Bang was the moment we crossed an event horizon, then the singularity we associate with the beginning of time would actually be the singularity at the center of a black hole. The universe would not have started from nothing. It would have started from the other side of an event horizon in some pre-existing space, and everything we observe, the expansion, the cooling, the formation of structure, would be the natural evolution of space-time inside that black hole. We would not be living in a universe that exploded outward from a point. We would be living in a universe that fell inward through a horizon, and the geometry we experience as expansion would actually be the inward curvature of space-time as it falls toward a singularity we have not reached yet. This is deeply uncomfortable. It flips the entire narrative. The Big Bang is supposed to be the moment everything began, the birth of time, the birth of space, the birth of matter and energy. If it was just an entrance, if it was the moment we crossed a boundary into a structure that already existed, then the universe is older than we thought. Not 13.8 billion years, infinitely old, or at least older by some unknowable amount that depends on what was happening on the other side of the event horizon before we fell through. And if that is true, then the singularity at the beginning of time is not the beginning at all. It is a feature of the geometry, a boundary in the equations, but not an origin in any meaningful sense. The Standard Model does not require this interpretation. You can take the Big Bang as a true beginning, a moment when time itself started, and the equations work fine. But you can also take the same equations, apply them to the interior of a black hole, and get a solution that looks almost identical. The metrics, the mathematical descriptions of the geometry, are related by a coordinate transformation. If you use one set of coordinates, you get the expanding universe. Use a different set, and you get the black hole interior. The physics does not change, the interpretation does. Here is a concrete way to see the parallel. Take the Friedmann equations, the ones that describe how the universe expands. They tell you how the scale factor, the thing that tracks the size of the universe, changes with time. In the standard Big Bang model, the scale factor starts at 0 and grows. Space expands, galaxies move apart, the universe gets bigger. Now take the equations that describe the interior of a Schwarzschild black hole, the simplest kind of black hole with no rotation and no charge. Inside the event horizon, there is a coordinate called the proper time, the time you would measure on a clock as you fall toward the singularity. As that time increases, space around you stretches, distances grow. Objects that were close together move apart, not because they are moving through space, but because the space between them is expanding. The geometry inside the black hole interior, described in these coordinates, looks like an expanding universe. The equations are the same. The behavior is the same. The only difference is the boundary conditions and the interpretation of what the singularity represents. If you were born inside a black hole and had no way to see outside it, you would measure the expansion of space around you and conclude you were living in an expanding universe. You would observe galaxies receding. You would measure redshifts. You would calculate a Hubble constant. You would build a cosmology based on the assumption that the universe began at some moment in the past when everything was compressed into a singularity, and you would be half right. The singularity would be real. The expansion would be real. But the interpretation, the idea that the singularity marked the beginning of time, would be wrong. The singularity would be in your future, not your past. You would be falling toward it, not expanding away from it. And the geometry you measured, the one that looked like an expanding cosmos, would actually be the interior of a black hole. Now ask yourself this: how would you know the difference? What measurement could you make? What observation could you perform that would tell you whether you were in an expanding universe or inside a black hole? The redshifts would be the same. The recession of galaxies would be the same. The cosmic microwave background would look the same. The abundances of hydrogen and helium would be the same. Every test the standard Big Bang model passes, the black hole interior interpretation would also pass, because they are describing the same geometry from different perspectives. The only way to tell them apart would be to look at something outside the event horizon, and by definition, you cannot do that. Information from outside the horizon cannot reach you. You are cut off, isolated, trapped inside a bubble of space-time from which no signal can escape, and into which no signal from beyond can enter. This is where the idea stops being a curiosity and starts being disturbing, because the observable universe is exactly that kind of bubble. We are surrounded by a horizon, the particle horizon, beyond which we cannot see. Light from regions farther than about 46 billion light-years away has not had time to reach us. We are isolated inside a spherical region of space, confined not by a wall, but by geometry and the finite speed of light. And the size of that region, the 46 billion light-year radius, matches the Schwarzschild radius for the total mass inside it. The numbers line up, the geometry fits. The boundary we call the edge of the observable universe could just as easily be called an event horizon, and we would not know the difference from the inside. If the Big Bang was an entrance, then the question everyone wants answered, what came before it, has an answer, not nothing. Not a meaningless question, but something, some other region of space-time, some other universe or structure from which we fell. The event horizon would mark the boundary between that region and ours. On one side, the outside universe, whatever it is, continues to exist and evolve. On the other side, inside the horizon, we live out our existence cut off from it, watching the geometry around us expand as we fall toward a singularity we will never reach because time itself ends there. This raises a cascade of new questions, none of which have satisfying answers. If we fell into a black hole, whose black hole is it? What universe does it belong to? What are the rules there? Are the laws of physics the same? Is the speed of light the same? Is gravity the same? We have no way to know. The event horizon separates us completely. Information cannot cross it, at least not in the direction we need. Anything happening outside the horizon is invisible to us, forever. We are sealed inside, with no way to communicate outward and no way to receive signals inward. The universe we observe, the one we measure and catalogue and try to understand, would be a bubble, a pocket, a region of space-time that has been cut off from the larger structure it came from. And here is the strangest part. If we are inside a black hole, then the singularity is not behind us, it is ahead of us. The Big Bang singularity, the one we think marks the beginning of time, would actually be in our future. We have not reached it yet. We are still falling toward it. The expansion of space we measure would not be the universe growing outward from an initial explosion. It would be the geometry stretching inward as we fall. The singularity would be at the end of time, not the beginning. And when we finally reach it, billions or trillions of years from now, depending on the exact geometry, space-time itself would end. Not in a crunch, not in a collapse, but in a termination. A boundary beyond which the concept of time no longer applies. The standard Big Bang model predicts something similar, at least in some versions of it. If the universe is closed, if it has enough mass to eventually halt the expansion and reverse it, then everything collapses back into a singularity in the far future. A big crunch. The end of time would mirror the beginning. The black hole interpretation just says that collapse is not a reversal of the expansion. It is the natural endpoint of a fall that started the moment we crossed the event horizon. The geometry forces it. You cannot escape it any more than you can escape next Tuesday. None of this is proven. The standard Big Bang model is not proven either, in the sense that we cannot rerun the universe and check whether it really started from a singularity. But the standard model fits the data. It explains the observations. It makes predictions that have been confirmed. The black hole interpretation fits the same data. It makes the same predictions. It is mathematically equivalent in most of the regimes we can test. The difference is philosophical. One interpretation says the universe began from nothing, or from a singularity that marked the start of time. The other says the universe began by crossing a boundary, by falling into a structure that already existed. Both are consistent with the equations. Both describe the same geometry. And we have no way, from inside the horizon, to tell which one is correct. What we do have are numbers that refuse to cooperate. The size of the observable universe matches the Schwarzschild radius for its mass. The expansion rate we measure matches the geometry of a black hole interior. The singularity at the beginning of time has the same mathematical form as the singularity at the center of a black hole. These could all be coincidences. Physics is full of coincidences that turn out to mean nothing. But physics is also full of coincidences that turned out to be clues. When the charge of the electron exactly balances the charge of the proton, that is not random. It reflects a deeper symmetry. When the cosmic microwave background has almost exactly the temperature and spectrum predicted by the Big Bang model, that is not luck. It is evidence the model is right. When the observable universe is exactly the size a black hole with its mass would be, that might be a coincidence. Or it might be the universe trying to tell us something we have been too stubborn to hear. The Big Bang as an entrance, not a beginning, is not a fringe idea in the sense that it violates known physics. It is a fringe idea in the sense that most physicists do not think it is necessary. The standard model works without it. Adding the black hole interpretation does not make new predictions that you could test. It does not solve problems the standard model cannot handle. It just reframes the story in a way that makes some of the numbers less coincidental and some of the questions less awkward. Why does the universe have a singularity at the beginning? Because singularities are what you get at the center of black holes, and we are inside one. Why is the observable universe exactly the size of a black hole event horizon? Because it is an event horizon. Why does the expansion of space look like the geometry inside a black hole? Because that is what we are measuring. The interpretation does not require new particles, new forces, new fields. It just requires taking general relativity seriously in a regime we usually do not think about. The inside of a black hole is a valid solution to Einstein's equations. The expanding universe is a valid solution to Einstein's equations. The fact that they can be mapped onto each other through a coordinate transformation is not a bug, it is a feature. It tells you that the boundary between what we call a universe and what we call a black hole is thinner than our intuition suggests. The equations do not care which label you use, they just describe the geometry. And the geometry we live in happens to match both descriptions at once. If the Big Bang was an entrance, then the ultimate question shifts. It is no longer, why is there something rather than nothing? It is, why did we fall through? What caused the event horizon to form? What was on the other side? Was there a collapse, a star or a galaxy, or something even larger that reached the end of its life and formed a black hole? And are we living inside the remnants of that collapse? Or was the event horizon always there, a permanent feature of some larger structure, and our universe is just one of many pockets that have fallen through over the eons? We do not know. We cannot know, at least not from inside the horizon. The geometry seals us off. The past beyond the Big Bang, if there is a past, is hidden on the other side of a boundary we cannot cross. And the singularity ahead of us, if the interpretation is right, is a wall we will eventually hit, not in our lifetimes. Not in the lifetime of any star currently burning, but eventually, if the geometry plays out the way the equations suggest, space-time itself runs out of road. The universe does not fade into cold darkness, it ends completely. At a singularity where the fabric of space and time breaks down and nothing on the other side is defined. The Standard Model has its own version of this problem. The singularity at the beginning of time is a place where the equations fail. The singularity at the end, if there is one, is the same. General relativity gives you these boundaries and then shrugs. Quantum gravity, if we ever figure it out, might replace the singularities with something smoother, something that does not blow up to infinity. But we do not have quantum gravity yet. We have general relativity, and general relativity says singularities are real. Whether they sit at the beginning of time or the center of a black hole, they are places where the theory stops and something new has to begin. The Big Bang reimagined as an entrance does not solve that problem. It just moves it. The singularity is still there. The breakdown of physics is still there. The equations still fail at the boundary, but the story changes. The universe stops being a miracle, a creation from nothing, and starts being a consequence. A region of space-time that fell through a horizon, evolved according to the rules of general relativity, and will one day reach the end of the geometry it is following. Whether that story is more satisfying than the standard one is a matter of taste. Whether it is true is a matter of math. And the math, for now, leaves both doors open. What we can say is this: the universe we live in has the size, the mass, the expansion rate, and the geometry of a black hole interior. Those are not interpretations, those are measurements. The numbers sit in the data, waiting for an explanation. The Standard Model explains them by saying the universe started from a singularity and has been expanding ever since. The black hole interpretation explains them by saying the universe crossed an event horizon and the expansion is a consequence of the interior geometry. Both stories fit the facts, both are consistent with general relativity, and both leave us with a cosmos that is stranger, larger, and more deeply connected to the fabric of space-time than any intuition built from everyday experience could have prepared us for. The Big Bang might not be the beginning. It might just be the moment we fell in. And if that is true, then every question we have been asking about where we came from needs to be rewritten from the ground up, because the answer is not behind us in time. It is on the other side of a horizon we crossed billions of years ago and can never see beyond. If the Big Bang was an entrance rather than a beginning, if we are living inside the geometry of a black hole interior, watching space expand as we fall toward a singularity hidden somewhere in our future, then we have a problem, a big one. It is called the information paradox, and it has been quietly tearing at the foundations of physics for more than 50 years. The problem is simple to state and impossible to solve with the tools we currently have. Information, according to the rules of quantum mechanics, cannot be destroyed, ever. You can scramble it, hide it, spread it across the universe in ways that make it effectively impossible to recover, but you cannot erase it. The laws of physics are reversible. If you know the state of a system now, and you know the laws that govern it, you can in principle calculate what the state was in the past, or what it will be in the future. That reversibility is baked into quantum mechanics at the deepest level. It is called unitarity, and it is one of the non-negotiable rules of the game. Break unitarity, and the entire framework collapses. Black holes, according to classical general relativity, do not care about unitarity. They swallow information. You throw a book into a black hole, and it crosses the event horizon. From the outside, the book is gone. You cannot see it. You cannot retrieve it. The information about every word on every page, every atom in the paper, every quantum state of every particle, all of it vanishes behind the horizon. The black hole does not remember what fell in. It only knows its mass, its charge, and its spin. 3 numbers. Everything else is erased. A black hole made by collapsing a star looks identical to a black hole made by collapsing 1,000,000 encyclopedias, as long as the total mass, charge, and spin are the same. The details do not matter. The information is lost. That is what classical general relativity says. Quantum mechanics says that is impossible. One of these theories has to be wrong or incomplete, or both. And for decades, nobody could figure out which. The story starts in the early 1970s with a graduate student named Jacob Bekenstein working at Princeton under the physicist John Wheeler. Wheeler was the one who coined the term black hole. He was also obsessed with the question of what happens to information when it falls into one. Bekenstein, following Wheeler's lead, started thinking about black holes as thermodynamic objects. Thermodynamics is the study of heat, energy, and entropy. Entropy is a measure of disorder, or, more precisely, a measure of how many different microscopic configurations a system could have that would all look the same from the outside. High entropy means lots of possible hidden arrangements. Low entropy means fewer. The second law of thermodynamics says entropy never decreases in a closed system. Things get messier over time, not cleaner. That is why ice melts and does not spontaneously freeze, why coffee cools and does not spontaneously heat up. The universe trends toward disorder. Bekenstein realized that if you throw something with entropy into a black hole, the entropy of the thing disappears. It crosses the horizon and is gone. That violates the second law. The total entropy of the universe goes down. Unless, Bekenstein thought, the black hole itself has entropy. If the black hole gains entropy when it swallows something, the second law is saved. But how much entropy should a black hole have? Bekenstein worked out that it should be proportional to the area of the event horizon, not the volume. The area. That was strange. Entropy usually scales with volume because it counts the number of possible states inside a region, and the number of states should grow with how much space you have to work with. But black holes are different. Their entropy grows with the surface area of the horizon. Double the radius of the event horizon, and the area goes up by a factor of 4, and so does the entropy. Bekenstein published his idea in 1972 and 1973, and it was met with skepticism. Stephen Hawking, in particular, thought it was wrong. If black holes have entropy, they must have temperature, and if they have temperature, they must radiate. But nothing can escape a black hole, so how could it radiate? Hawking set out to prove Bekenstein wrong. He failed. What he found instead, in 1974, was that black holes do radiate, not because anything escapes from inside the event horizon, but because of quantum effects right at the horizon itself. Empty space is not really empty. It is filled with quantum fluctuations, pairs of particles and antiparticles that pop into existence and annihilate each other almost instantly. Near the event horizon of a black hole, one particle from a pair can fall in while the other escapes. To an outside observer, it looks like the black hole is emitting particles. That emission is now called Hawking radiation. The radiation has a temperature, and the temperature is inversely proportional to the mass of the black hole. Small black holes are hot, large black holes are cold. The black hole at the center of the Milky Way, weighing about 4 million times the mass of the Sun, has a temperature of about 1/1000th of a degree above absolute zero. A black hole the size of the observable universe would have a temperature so low it is effectively zero. But a tiny black hole, one with the mass of a mountain compressed into the size of a proton, would glow white hot and evaporate in a fraction of a second. Hawking calculated the temperature and confirmed Bekenstein's formula for the entropy. The entropy of a black hole is proportional to the area of its event horizon divided by 4 times the Planck length squared. The Planck length is the smallest meaningful distance in physics, about 10 to the minus 35 meters. It is the scale at which quantum effects and gravitational effects become equally important, and where space-time itself is thought to break down into some kind of quantum foam. The formula is usually written as S equals K times C cubed times A divided by 4 times G times H bar, where S is entropy, A is the area of the event horizon, K is Boltzmann's constant, C is the speed of light, G is the gravitational constant, and H bar is the reduced Planck constant. The details of the formula are not important for this story. What matters is that the entropy scales with area, not volume. A black hole stores its information on its surface, not in its interior. Hawking's discovery created a paradox. If black holes radiate, they lose mass. As they lose mass, they shrink. Eventually, they evaporate completely. A black hole the size of the Sun would take about 10 to the 67 years to evaporate, far longer than the current age of the universe. But in principle, it happens. The black hole radiates away all its mass and disappears. The question is, what happens to the information that fell in? The Hawking radiation, as originally calculated, is thermal. It has a temperature, but it carries no information about what fell into the black hole. It is random noise. If the black hole evaporates and all that is left is random radiation, the information about everything that fell in is gone, destroyed. That violates unitarity. Quantum mechanics says information cannot be destroyed, but black holes seem to destroy it anyway. This is the information paradox. For decades, it split the physics community into camps. Some, including Hawking himself for many years, argued that information really is destroyed. Black holes are places where quantum mechanics breaks down and unitarity does not hold. Others, led by Leonard Susskind and Gerard Hooft, argued that information must be preserved somehow. The radiation cannot be truly thermal. There must be correlations, subtle patterns encoded in the radiation that carry the information out. The disagreement was not just technical. It was philosophical. If information can be destroyed, the universe is fundamentally unpredictable. You cannot reconstruct the past from the present. The laws of physics are not reversible. If information is preserved, then even black holes, the most extreme objects in the universe, play by the same rules as everything else. The turning point came from an idea called the holographic principle. It was developed in the 1990s by T. Hooft and Susskind, building on the connection between entropy and area that Bekenstein and Hawking had discovered. The principle says that all the information contained in a region of space can be encoded on the boundary of that region, not inside the region, on its surface. Think of it like a hologram. A hologram is a flat, two-dimensional surface that encodes a three-dimensional image. When you shine light through it, the image appears to have depth. The information about the three-dimensional structure is stored in 2 dimensions. The holographic principle says the universe works the same way. The physics inside a volume of space can be fully described by information on the surface of that volume. The interior is not fundamental, the boundary is. This sounds like a mathematical trick, but it has been tested in specific cases, and it works. The most famous example is something called the AD-S-CFT correspondence, discovered by Juan Maldacena in 1997. AD-S stands for anti-de Sitter space, a kind of negatively curved spacetime that shows up in string theory. CFT stands for conformal field theory, a type of quantum theory that lives on the boundary of that space. Maldacena showed that a theory of gravity in a five-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory on the four-dimensional boundary. Every gravitational event in the bulk, every black hole, every collision, every ripple in spacetime corresponds to some process in the boundary theory. The information is not lost, it is encoded on the boundary. The holographic principle is not just a metaphor. In this case, it is an exact mathematical duality. Our universe is not anti-de Sitter space. It is closer to de Sitter space, which has positive curvature and is expanding. So the AD-S-CFT correspondence does not apply directly to the cosmos we live in, but the principle does. If black holes obey the holographic principle, and black holes are just extreme curvatures of spacetime described by the same equations that describe the universe, then maybe the universe itself is holographic. Maybe all the information about everything happening inside the observable universe is encoded on a two-dimensional surface at the boundary. Maybe the three-dimensional space we experience is not fundamental. Maybe it is a projection, a hologram, generated by physics happening on a distant horizon. If we live inside a black hole, this starts to make sense in a disturbing way. A black hole's entropy scales with the area of its event horizon. The information about everything inside the black hole is stored on that horizon. The interior, the region we would be living in, does not contain the information. It is a derived structure, a kind of holographic shadow cast by the physics on the boundary. If the observable universe is the interior of a black hole, then the information about everything in our universe, every galaxy, every star, every atom, every thought you have ever had, is encoded on the event horizon, not inside the universe, on its edge. The three-dimensional cosmos you experience, the space you move through, the time you age through, all of it would be an emergent phenomenon. The real physics happens on the boundary. The interior is just the hologram. This is not a mainstream interpretation. Most cosmologists do not spend time thinking about whether the universe is a hologram projected from a distant event horizon, but the math allows it. General relativity and quantum mechanics, when combined in the framework of the holographic principle, point toward this possibility. The numbers line up. The observable universe is 93 billion light-years across. Its Schwarzschild radius, the radius an event horizon would have if all the mass inside it were compressed into a black hole, is about 46 billion light-years. The match is not exact to arbitrary precision, but it is close enough to make you stop and think. If the universe is a black hole, its entropy should scale with the area of the event horizon. The event horizon of the observable universe would have an area of about 10 to the 123 square Planck lengths. That is an enormous number. The entropy of the observable universe, if you add up the entropy of all the matter, all the radiation, and all the black holes inside it, is estimated to be around 10 to the 122 or 10 to the 123, depending on how you count. The numbers match. The entropy of the universe is consistent with it being the interior of a black hole, whose event horizon has exactly the area we would calculate from its size and mass. None of this proves we are living in a hologram, but it does mean the idea is not ruled out. The equations that describe black holes and the equations that describe the universe are the same equations. If black holes store information on their surfaces, and the universe has the size and mass of a black hole, then the universe might store information on its surface too. The boundary of the observable universe, the particle horizon beyond which we cannot see, could be an event horizon. And the physics we observe, the matter and energy and space-time inside that horizon, could be a holographic projection from the two-dimensional boundary. Here is where things get deeply strange. If the universe is a hologram, then space is not fundamental. Space is something that emerges from the information encoded on the boundary. The three dimensions you experience, up, down, left, right, forward, back, are not the basic structure of reality. They are a convenient description, a way of organizing the information, but the underlying reality is two-dimensional. The third dimension, and time as well, are emergent. They arise from correlations and entanglement in the boundary theory. This is not science fiction. This is a serious proposal, studied by theoretical physicists working on quantum gravity. The idea is that space-time itself is not fundamental. It is a derived concept, something that appears when you coarse-grain over the microscopic quantum information. If you live inside a hologram, you would not know it. You would measure distances in 3 dimensions. You would feel like you are moving through space. Clocks would tick. Objects would have volume. The hologram would be perfect. There would be no glitch, no seam, no way to detect from the inside that the 3-dimensional world you experience is actually being generated by 2-dimensional physics on a distant boundary. The only clue would be in the math. The only hint would be that the entropy scales with area instead of volume. And that is exactly what we see with black holes. The implications for causality are unsettling. Causality is the rule that says effects follow causes. If you drop a glass, it falls and breaks. The dropping causes the breaking. Time flows forward and causes precede effects. But if the universe is a hologram, causality might not work the way you think it does. Events that seem causally connected in the 3-dimensional interior might not be connected on the 2-dimensional boundary. The boundary theory has its own structure, its own rules for how information propagates. When you translate that into the 3-dimensional hologram, you get what looks like ordinary causality. Objects move, forces act, time flows. But the underlying description, the one on the boundary, might not have the same causal structure. Events that appear to happen at different times in the interior might correspond to simultaneous processes on the boundary. The arrow of time, the thing that makes the future different from the past, might be an artifact of how the hologram is projected, not a fundamental feature of reality. This is speculative, but it is taken seriously enough that there are research programs dedicated to understanding how space-time emerges from quantum information. If space is not fundamental, then the familiar concepts of distance, volume, and geometry are approximations. They work well in the regime we can observe, where space-time is smooth and well-behaved. But near singularities, near the Big Bang, or inside black holes, space-time breaks down. The holographic description might remain valid even when the geometric description fails. The information is still there, encoded on the boundary, even when the interior geometry becomes infinite or undefined. If our universe is a hologram projected from the event horizon of a larger black hole, then the singularity at the beginning of time, the Big Bang, is not a place where information was created. It is a place where the hologram started. The boundary theory has its own initial conditions, and those conditions determine the state of the interior. The singularity is a feature of the holographic projection, not a feature of the underlying physics. The real initial state is on the boundary, and the Big Bang is what happens when you project that state into 3 dimensions. The universe did not begin with a bang, the hologram did. The black hole information paradox in this framework is solved. Information never falls into a black hole in a way that destroys it. From the perspective of the boundary theory, the information is always there. It is encoded in the degrees of freedom on the horizon. When Hawking radiation is emitted, it carries correlations that encode the information about what fell in. The radiation looks thermal if you only measure a few particles, but if you could collect all the radiation over the entire evaporation process, you would find that it contains all the information. The paradox arises because we were thinking about black holes as 3-dimensional objects with an interior and an exterior. But if black holes are holographic, the interior is not fundamental. The information is on the surface, and the radiation is how that information gets transferred back out. This resolution was proposed decades ago, but it was not widely accepted until recently. In 2019 and 2020, a series of papers calculated something called the Page curve, named after the physicist Don Page. The Page curve describes how the entropy of Hawking radiation changes as a black hole evaporates. Early in the evaporation, the entropy of the radiation increases. More and more particles are emitted, and the radiation becomes more disordered. But at some point, the curve turns around. The entropy starts decreasing. The radiation becomes more ordered. By the time the black hole has completely evaporated, the total entropy of the radiation matches the entropy of whatever fell in. The information has been recovered. The calculation that produced the Page curve used tools from quantum gravity and holography, and it showed that the information is never lost. It is always encoded, first on the horizon, then gradually transferred into the radiation. Stephen Hawking, before he died, came around to this view. For years, he had argued that information is destroyed. In 2004, he gave a talk at a conference in Dublin where he conceded the point. He admitted he had been wrong. Information is preserved. Black holes do not destroy it. The mechanism is subtle and involves quantum correlations that are not obvious in the classical picture, but the information comes out. The paradox is resolved, at least in principle. The details are still being worked out, but the consensus among physicists working on quantum gravity is that unitarity holds. Information is never destroyed, not even by black holes. If we live inside a black hole, this means the information about our universe is not stored inside it. It is stored on the event horizon. And if the event horizon is holographic, then every atom, every photon, every bit of data in the observable universe corresponds to some microscopic degree of freedom on a 2-dimensional surface 46 billion light-years away. The observable universe would be a projection from that surface, a hologram so detailed and so convincing that we would never know the difference unless we could somehow access the boundary and read the information directly, and we cannot. The boundary is beyond the particle horizon. Light from the boundary has not reached us and never will. We are sealed inside, living out our existence in a hologram, with no way to verify from the inside whether the projection is real or whether there is a more fundamental description on a surface we can never see. This is not proof that we live in a hologram. It is not proof that the universe is the interior of a black hole, but it is proof that the question is not absurd. The math allows it. The holographic principle, which started as a way to resolve the information paradox for black holes, has grown into a framework for understanding space-time itself. If space-time is emergent, if it arises from information encoded on a boundary, then the universe we observe is not the deepest level of reality. There is something underneath, something simpler, something that does not involve space or time at all, just pure information. And everything we see, everything we experience, is a hologram projected from that information. The universe might be a book written on a surface. The pages are the event horizon. The words are the microscopic quantum states. And the story, the three-dimensional cosmos with its galaxies and stars and planets and people, is what you get when you read the book. The book is real, the story is real, but the book is more fundamental, and if you are a character in the story, you will never see the pages. You will only see the story unfolding around you, obeying the rules written into the book, with no way to step outside and read the text yourself. If this is true, it means the observable universe is not just a region of space we happen to be able to see. It is a holographic projection from a boundary we cannot access. The Big Bang was not the beginning of time, it was the beginning of the hologram. And the singularity at the end, if there is one, is not the end of time. It is the moment the hologram stops. The boundary keeps existing, the information keeps existing, but the projection ends. Space-time itself, the thing we move through and measure and map, comes to an end. Not because the universe collapses or fades, but because the geometry that generates the hologram runs out. The story reaches its last page, and the book closes. And whatever reality exists beyond the book, beyond the hologram, beyond the event horizon, is something we cannot see, cannot measure, and cannot imagine, because we are made of the projection. We are characters in the hologram, and the pages that encode us are written on a surface that lies forever outside the universe we can ever observe. The information paradox taught us that black holes do not destroy information, they hide it on their surfaces. The holographic principle taught us that the surfaces are enough. You do not need the interior. The boundary contains everything. And if the universe is a black hole, then we are living in the interior, and everything we know, everything we are, is encoded on a boundary we will never reach. That boundary is not empty space. It is packed with information, more information than every book ever written, every star that ever burned, every thought anyone has ever had. All of it compressed into a two-dimensional surface, generating a three-dimensional hologram so convincing that we call it reality. And the math says this is possible, not proven, but possible. And in physics, possible is sometimes the most terrifying word there is. If the universe we live in is the interior of a black hole, then the question that keeps physicists awake at night is not what happens to us, it is what happens next. Because if our universe can be a black hole viewed from the inside, then every black hole in our universe might contain a universe of its own, a cosmos born from collapse, a Big Bang triggered by the formation of an event horizon, a chain of creation that never ends, stretching backward and forward through an infinite hierarchy of nested realities, each one seeded by the death of matter in the universe above it. This is not idle speculation. This is a testable hypothesis, or at least it was supposed to be when a physicist named Lee Smolin first proposed it in the early 1990s. He called it cosmological natural selection, and the idea is as elegant as it is disturbing. Start with what we know. Black holes form when massive stars collapse. The core runs out of fuel, the outward pressure from fusion stops, and gravity takes over. The star implodes. If the core is heavy enough, nothing can stop the collapse. Electrons get crushed into protons, forming neutrons. Then even the neutrons cannot hold. The core collapses past the neutron degeneracy pressure, past every known mechanism that could resist gravity, and it keeps collapsing. At some point, the curvature of spacetime becomes so extreme that an event horizon forms, a boundary in spacetime where escape becomes impossible. The matter inside continues to collapse, heading toward a singularity where density becomes infinite and the equations break. That singularity is hidden behind the event horizon, invisible from the outside, sealed off from the rest of the universe by the geometry of spacetime itself. From the perspective of someone outside the black hole, that is the end of the story. The star collapses, the event horizon forms. The black hole settles into a stable configuration defined by its mass, charge, and spin. The interior is gone, hidden, cut off. You cannot see it. You cannot access it. You cannot communicate with it. The only things that matter are the numbers that describe the black hole from the outside. 3 parameters, that is it. Everything else, every detail about the star that collapsed, every atom, every quantum state, all of it is erased from the external universe. The black hole is a blank slate, but from the perspective of someone falling into the black hole, the story is very different. Time dilation becomes extreme near the event horizon, but once you cross it, you are inside a region of spacetime where the inward direction is no longer a direction in space, it is a direction in time. You are moving toward the singularity not because something is pulling you, but because the singularity is in your future. And as you fall, space around you behaves in ways that look a lot like an expanding universe. Distances grow. Objects that were close together move apart. The geometry stretches. Smolin took this seriously. He asked what happens at the singularity. General relativity says the curvature becomes infinite. The equations fail. The theory breaks down. But general relativity is a classical theory. It does not include quantum mechanics. And at the scales where singularities form, quantum effects cannot be ignored. The Planck length, about 10 to the minus 35 meters, is the distance at which quantum fluctuations of spacetime itself become significant. At those scales, the smooth geometry of general relativity is no longer a good description. Spacetime becomes a quantum foam, a chaotic mess of virtual black holes and wormholes popping in and out of existence. Nobody knows exactly what happens there because we do not have a working theory of quantum gravity. But one possibility, explored by Smolin and others, is that the singularity does not collapse to a point of infinite density. Instead, it bounces. The collapse halts. The curvature reaches a maximum and then reverses. The contracting region rebounds, expanding outward again, not into the universe it came from, into a new region of spacetime, a new universe. The bounce is not arbitrary. It is a consequence of quantum effects becoming strong enough to resist gravity at extremely small scales. In loop quantum gravity, one of the candidate theories for quantum gravity, there is a mechanism that prevents singularities. The geometry cannot shrink past a certain point. When you try to compress spacetime to Planck scale densities, the quantum structure resists. The collapse stops and reverses. What was falling inward starts expanding outward. The singularity is replaced by a bounce. And on the other side of the bounce, you have a new region of spacetime that looks like the early universe. Hot, dense, expanding, a big bang. If this is true, then every black hole that forms in our universe is not just an endpoint, it is a seed, a nursery for a new cosmos. The collapse that creates the event horizon is also the event that triggers the Big Bang in the universe inside. From our perspective, the black hole is a stable object sitting in space, pulling in matter and light. From the perspective of someone inside, the Big Bang just happened. Time started. Space is expanding. The conditions for stars and galaxies and planets are being set. A whole universe is unfolding, sealed off from ours by the event horizon, evolving according to its own rules. Smolin went further. He proposed that the laws of physics in the new universe might not be exactly the same as in the parent universe. When the bounce happens, when the singularity rebounds and a new space-time is born, the parameters that define the laws of physics, things like the strength of gravity, the masses of fundamental particles, the value of the cosmological constant, might get randomized slightly. Not completely. There is continuity. The new universe inherits most of the structure of the parent, but there is room for variation. Small changes, mutations, if you want to use biological language, and if there are mutations, there can be selection. Some combinations of physical parameters will produce universes that are good at making black holes. Those universes will have lots of massive stars that collapse and form event horizons, each one seeding a new universe. Other combinations will produce universes where stars do not form, or where they form but do not collapse into black holes. Those universes will have few or no offspring. Over time, over an unimaginably long sequence of generations, the universes that are best at making black holes will dominate. Not because anyone is choosing them, just because they produce more descendants. It is natural selection applied to cosmology. The fittest universes, the ones whose laws allow for abundant black hole formation, reproduce more often and come to dominate the population of all possible universes. This is cosmological natural selection, and it makes a testable prediction. If our universe is the product of this process, if it has been shaped by selection over many generations, then the laws of physics we observe should be tuned to maximize black hole production. Not perfectly. There is randomness, there is variation. But on average, our universe should be sitting near the peak of the black hole production landscape. Change the laws of physics slightly, tweak the parameters in almost any direction, and you should get fewer black holes. That is the prediction. Smolin checked this. He looked at the parameters that determine how stars form and evolve. The strength of the strong nuclear force, which holds atomic nuclei together, the mass of the electron, the mass of the neutron, the value of the fine structure constant. He found that small changes in most of these parameters would either prevent stars from forming or prevent them from collapsing into black holes. Strengthen the strong force slightly, and stars burn out too fast. Weaken it, and nuclei fall apart. Increase the electron mass, and atoms become too heavy. Decrease it, and chemistry breaks. The range of values that allows for stars and black holes is narrow. Our universe sits inside that range, not at the exact center, but close enough that Smolin could argue the fit is not random. It looks like the result of optimization. This is provocative. It suggests the universe we live in has been shaped by a process that resembles evolution. Not biological evolution, cosmological evolution. Universes that produce black holes spawn more universes, universes that do not die out. Over many generations, the population of universes shifts toward configurations that are good at making black holes. And because black holes require stars, and stars require planets, and planets are where life can arise, the same process that optimizes for black hole production also creates the conditions for complexity, for chemistry, for biology, for observers. You do not need to invoke a designer or fine-tuning from outside. The tuning happens naturally through a process of variation and selection playing out across a vast ensemble of universes. The idea has critics, a lot of them. One problem is that nobody knows whether the bounce actually happens. Loop quantum gravity predicts it, but loop quantum gravity is not a complete theory. It has not been tested experimentally. String theory, the other major candidate for quantum gravity, does not obviously predict a bounce. In string theory, singularities might be replaced by extended objects, like strings or branes, but whether those objects give rise to new universes is unclear. The math is hard and the predictions are ambiguous. Until we have a working theory of quantum gravity that everyone agrees on, the bounce remains speculative. Another problem is the randomization of parameters. Smolin assumes the physical constants can vary when a new universe is born, but nobody knows if that is true. The constants might be fixed. They might be determined by some deeper principle that does not allow variation. If the laws of physics are unique, if there is only one self-consistent set of parameters, then there is no room for selection. Every black hole would spawn a universe with the same laws as the parent. The process would repeat identically, and there would be no evolution, no optimization, just an infinite chain of identical copies. The third problem is observational. How do you test this? If every black hole contains a universe, and every universe is sealed off from its parent by an event horizon, then you cannot look inside and check. You cannot send a probe into a black hole and report back. You cannot communicate with the universe inside. The event horizon is a one-way membrane. Information can cross inward, but nothing can cross outward. From the perspective of the parent universe, the interior of a black hole is invisible. From the perspective of the interior, the parent universe is in the past, on the other side of the horizon, forever out of reach. The theory makes predictions about the distribution of physical parameters across the population of universes, but we only have access to one universe, ours. We cannot sample the ensemble. We cannot measure the variance. We cannot check whether the distribution looks like what natural selection would produce. Smolin tried to work around this. He argued that the prediction is not just about the ensemble, it is about our universe specifically. If cosmological natural selection is real, and if our universe is a product of it, then the laws of physics we measure should be near a local maximum for black hole production. You should not be able to tweak the parameters in most directions without reducing the number of black holes. That is a testable claim, at least in principle. You build models of stellar evolution. You vary the parameters. You count how many stars collapse into black holes. You check whether our universe is near the peak. Smolin did this and found that small changes in most directions reduce black hole production. The fit is not perfect. There are some directions in parameter space where you can increase black hole production slightly, but overall, our universe looks optimized. That is evidence, he argued, that the theory is right. Critics pointed out that the calculation depends on assumptions. You have to model stellar evolution. You have to decide which parameters to vary and by how much. You have to estimate how many black holes form in a given universe, and that depends on the initial conditions, the distribution of matter, the rate of star formation, all of which are uncertain. Change the assumptions, and the conclusion changes. The evidence is suggestive, but not conclusive. And even if the calculation holds up, it does not prove the theory. It just shows that our universe is consistent with being optimized for black hole production. That could be a coincidence, or it could be explained by some other principle, anthropic reasoning, for example. If only universes with certain parameters allow for observers, then observers will always find themselves in universes with those parameters, regardless of whether there was selection. The anthropic argument goes like this. Imagine a vast ensemble of universes with different laws of physics. Most of them are hostile to life. No stars, no planets, no chemistry, no observers, but a few, by chance, have parameters that allow for stars and planets and complexity. Observers can only arise in those universes. So when an observer asks why the laws of physics are tuned to allow for their existence, the answer is simple. If they were not tuned that way, there would be no observer to ask the question. It is a selection effect. You are sampling from a biased set. The universes you can observe are, by definition, the ones capable of producing observers. That explains the apparent fine-tuning without requiring cosmological natural selection. You do not need black holes to spawn new universes. You just need a large ensemble of universes with varying parameters, and the anthropic principle does the rest. Smolin does not like the anthropic argument. He thinks it is lazy. It explains too much. You can use anthropic reasoning to explain any parameter by saying it has to be that way for observers to exist. But it does not give you a mechanism. It does not tell you why there is an ensemble of universes in the first place, or how the parameters get varied, or what determines the distribution. Cosmological natural selection, by contrast, gives you a mechanism. Black holes spawn new universes. Parameters vary slightly. Selection favors configurations that produce more black holes. The distribution evolves over time. The anthropic principle is a tautology. Natural selection is a process. One is passive, the other is active. And in Smolin's view, science should favor active mechanisms over passive ones. The debate has not been resolved. Both sides have arguments. Both sides have problems. And in the absence of direct evidence, the question comes down to philosophy. Do you prefer a theory that explains the fine-tuning of physical parameters through a historical process of variation and selection? Or do you prefer a theory that explains it through observer selection on a static ensemble? Neither option is obviously wrong. Neither is obviously right. The math allows both. The observations do not distinguish them. And until someone figures out how to test the interior of a black hole or measure the distribution of physical parameters across the multiverse, the question stays open. But there is another angle to this story, and it involves white holes. If black holes are the entrance to new universes, where is the exit? General relativity allows for a solution called a white hole, which is the time-reversed version of a black hole. A black hole is a region of space-time where nothing can escape. A white hole is a region where nothing can enter. Matter and light can only flow outward from a white hole, never inward. The event horizon of a white hole is the same geometric structure as the event horizon of a black hole, just with the direction of time reversed. In a black hole, the singularity is in your future. In a white hole, the singularity is in your past. You cannot fall into a white hole because the geometry prevents inward motion. You can only be expelled from it. White holes have never been observed. They are mathematically allowed by general relativity, but there is no known mechanism for forming one. A black hole forms when matter collapses. What process would create a white hole? The standard answer is none. White holes are thought to be unstable. Even if one formed, it would not last. Perturbations, small ripples in spacetime, would destabilize it almost instantly. The event horizon would collapse, or the white hole would turn into a black hole, or it would explode. There is no steady-state white hole solution that can survive in a realistic universe, so most physicists treat white holes as mathematical curiosities, allowed by the equations, but not present in nature. Except there is one place where a white hole might exist, on the other side of the bounce. If the singularity inside a black hole rebounds and creates a new expanding region of spacetime, that rebound could look like a white hole from the perspective of the new universe. The Big Bang, in this picture, is not a singular event where time starts. It is the white hole exit point where matter and energy expelled from the parent universe begin expanding into the new universe. The event horizon of the black hole in the parent universe corresponds to the event horizon of the white hole in the baby universe. They are the same structure, viewed from opposite sides. Cross the black hole horizon from the outside and you fall into a collapsing region. Cross the white hole horizon from the inside and you see an expanding region. The two are connected by the bounce. The singularity that would have been the endpoint of the collapse becomes the starting point of the expansion. The black hole in the parent universe births a white hole in the baby universe, and the white hole is the Big Bang. This is elegant. It solves the singularity problem. It connects black holes and cosmology. It gives a mechanism for universes to reproduce, but it also raises new questions. If the Big Bang is a white hole, why do we not see white holes in our universe? If every black hole spawns a universe with a white hole at its origin, and if black holes are common in our universe, why have we never detected a white hole? The answer might be that white holes are short-lived. The Big Bang happened 13.8 billion years ago. If it was a white hole, it lasted for a brief moment, expelled the matter and energy that would become our universe, and then disappeared. By the time we came along, billions of years later, the white hole was long gone. All that remains is the expanding universe it created. We see the aftermath, not the event itself. Another answer is that white holes might still exist, but they look like something else. A white hole expels matter and energy. That looks like an explosion, a burst of particles and radiation streaming outward from a central point. Astronomers see bursts like that all the time: gamma-ray bursts, supernovae, quasars. Any of those could be white holes, and we would not know the difference unless we could get close enough to measure the geometry of space-time around the event. And even then, the signature might be ambiguous. A white hole and a black hole have similar geometries. The distinction is in the direction of information flow. Black holes let information in, but not out. White holes let information out, but not in. If you are observing from a distance, both can look like points of extreme curvature with matter and radiation streaming away. The devil is in the details, and the details are hard to measure. There is also the question of where the matter comes from. A white hole expels matter, but that matter has to come from somewhere. In the black hole births universe scenario, it comes from the parent universe. The matter that fell into the black hole gets processed by the bounce and expelled into the baby universe. The total mass energy is conserved, or at least transferred. What goes into the black hole comes out through the white hole. But the geometry is tricky. From the perspective of the parent universe, the matter fell into the black hole and is gone. From the perspective of the baby universe, the matter appeared out of the Big Bang. The two events are causally connected, but they are separated by an event horizon. The connection exists in the geometry, but it cannot be observed from either side. The parent universe cannot see the baby. The baby cannot see the parent. The event horizon seals the two off from each other. This leads to the idea of an infinite hierarchy. If our universe is the interior of a black hole in a parent universe, and if every black hole in our universe spawns a baby universe, then the structure is recursive. Our parent universe might itself be the interior of a black hole in a grandparent universe, and that grandparent universe might be inside a great-grandparent universe, and so on, infinitely upward and infinitely downward. Every black hole we observe, every stellar collapse, every supermassive black hole at the center of a galaxy could be the seed for a universe of its own. Those universes would have black holes of their own, which would spawn more universes, which would spawn more black holes forever. An infinite tree of nested realities, each one branching into many, each branch sealed off from the others by event horizons. The implications are staggering. If this is true, then the number of universes is not just large, it is infinite, and the structure is self-similar. Every layer looks like every other layer. Black holes at one level become Big Bangs at the next. The geometry repeats, the process repeats. It is a fractal cosmos where the pattern reproduces at every scale. You could zoom in forever, descending through layer after layer of nested universes, and you would never reach a bottom. You could zoom out forever, ascending through parent after parent, and you would never reach a top. The structure has no beginning and no end. It just is, eternal, infinite, self-generating. This is not a new idea, by the way. Versions of it have been proposed by multiple physicists over the decades. Smolin's cosmological natural selection is one version. André Linde's eternal inflation is another, though it uses a different mechanism. In Linde's picture, inflation never stops. It keeps going in some regions of space, spawning bubble universes that pinch off and evolve independently. Each bubble is a universe. The bubbles keep forming forever. The structure is infinite and self-reproducing, just like the black hole births universe scenario. The details differ, but the conclusion is the same. The cosmos is vastly larger and more complex than the single expanding universe we observe. Our universe is one bubble, one black hole interior, one branch on an infinite tree, and we have no way to see the rest of the tree. We are stuck on our branch, observing only the local region of spacetime we can access, with event horizons sealing us off from everything beyond. The question is whether any of this is testable. Smolin's prediction about black hole production is one test, but it is indirect and depends on assumptions. A more direct test would be to look for signatures in the cosmic microwave background, the afterglow of the Big Bang. If the Big Bang was a white hole connected to a black hole in a parent universe, the geometry might leave imprints in the distribution of temperature fluctuations in the microwave background, anomalies, patterns that do not fit the standard inflationary model. Some researchers have looked for these. They have found a few anomalies like the cold spot, a large region of the sky where the microwave background is slightly colder than average. Nobody knows what caused it. It could be a statistical fluctuation. It could be a foreground effect, something between us and the background. Or it could be a signature of the Big Bang being something other than a smooth singularity. A hint that the geometry is more complicated than we assumed. A clue that we are inside a black hole. Another test involves gravitational waves. If black holes spawn universes, the process might produce ripples in spacetime that propagate outward. Those ripples would be gravitational waves, and if they are strong enough, they might be detectable. The problem is that the waves produced by the bounce would be at frequencies far outside the range of current detectors. LIGO detects waves from colliding black holes and neutron stars with frequencies of tens to thousands of hertz. Waves from a quantum bounce at the Planck scale would have frequencies of 10 to the 43 hertz or higher. No detector we can build would catch them. But there might be indirect effects. The waves could interact with the cosmic microwave background, leaving a signature in the polarization of the light. That signature would be subtle, but it might be measurable with future experiments. Several groups are working on this. No detection yet, but the possibility is there. A third test involves the distribution of black holes. If cosmological natural selection is real, the parameters of our universe should be tuned to maximize black hole production. That means the number of black holes we observe should be near the upper limit of what is possible given our laws of physics. If we find that small changes in parameters could produce many more black holes, that would be evidence against the theory. If we find that we are near the peak, That would be evidence in favor. The calculation is difficult because it requires modeling the entire history of star formation and collapse across the observable universe. But it is doable, at least in principle. Some groups have attempted it. The results are inconclusive. The uncertainties are large, but the framework is there. The test could be refined. With better data, better models, and better understanding of stellar evolution, the question might be answerable within a few decades. The most unsettling part of the black hole births universe idea is not the mechanism, it is the implications. If every black hole spawns a universe, and if every universe spawns black holes, then the cosmos is not just infinite, it is alive, not in the biological sense. In the sense that it reproduces, it evolves, it changes over time. Universes are born, they grow, they form stars and galaxies and black holes. Those black holes spawn new universes. The new universes grow and spawn more black holes. The process repeats, the structure grows, it branches, it diversifies, and it never stops. There is no endpoint, no final state. Just an endless cycle of creation, driven by the collapse of matter and the rebound of singularities, playing out across an infinite hierarchy of nested spacetimes. We are part of that cycle. Our universe, our galaxy, our solar system, our planet, every atom in your body is a product of a process that has been running for who knows how long. Not 13.8 billion years, maybe trillions of years, maybe infinitely long, and it will keep running long after we are gone. Stars will collapse, black holes will form, new universes will be born, and somewhere in one of those universes, billions of years from now, some observer will look up at the sky and ask the same questions we are asking. Where did we come from? Why are we here? What happens next? And they will have no idea that their entire cosmos is the interior of a black hole in a universe that came before. Just like we have no idea whether we are. The chain stretches backward and forward infinitely. Every black hole a seed, every universe a branch. And the tree keeps growing, because the process that builds it is built into the fabric of space-time itself. Collapse, bounce, expansion, repeat. That is the engine, that is the mechanism. And if it is real, then the cosmos is not a thing, it is a process. A cycle of creation and destruction running forever, with no beginning and no end, generating an infinite hierarchy of universes nested inside black holes, nested inside universes, all of them sealed off from each other by event horizons, all of them following the same laws, or nearly the same laws, each one a variation on the theme, each one producing black holes that spawn more universes that produce more black holes, on and on, forever. And we are not observers standing outside this process, looking in. We are part of it, products of it. Participants in a cycle we did not choose and cannot escape, living out our brief existence in one tiny bubble of space-time, on one branch of an infinite tree, with no way to see the rest of the structure and no way to know how deep the nesting goes. If this is true, then the question we should be asking is not whether we are inside a black hole, it is how many layers deep we are. How many times has the cycle repeated? How many parent universes are there, stacked above ours, each one invisible, each one sealed off by an event horizon we can never cross? And how many baby universes are there, spawned by the black holes in our own cosmos, growing and evolving right now, completely unaware that they are nested inside a structure vastly larger than anything they can observe? The answer might be infinite. The nesting might go on forever, in both directions, up and down, parent and child, black hole and universe, collapse and expansion. The Ouroboros eating its own tail, except the tail is also the head, and the snake is an infinite fractal that repeats at every scale. That is the picture, and the math leaves the door open for it to be real. If every black hole spawns a universe, and every universe spawns black holes, and those black holes spawn more universes in an infinite recursive chain that has no beginning and no end, then the question we keep circling back to is the one we started with. The one that refuses to go away no matter how many layers we peel back. Where are we in all of this? Not in some grand cosmic sense where you draw a map with arrows and labels. In the immediate, practical, undeniable sense of what it means to exist inside a structure you cannot see beyond, cannot escape from, and cannot fully understand. We are here, wherever here is, and here has a shape, a geometry, a set of boundaries that are not walls we can touch, but limits encoded in the fabric of space-time itself. Those boundaries define what we can see, what we can reach, what we can know, and if the numbers are telling us anything, they are telling us that those boundaries look an awful lot like the interior of a black hole. The mathematical alignments are not subtle. They are sitting in plain sight, printed in every cosmology textbook, taught in every undergraduate course on general relativity, and somehow nobody wants to talk about what they actually mean. The observable universe is 93 billion light-years across. The Schwarzschild radius for the total mass energy inside that region is roughly 46 billion light-years. Those numbers match, not approximately, not in the right ballpark. They match within the uncertainties of the measurements we use to estimate the universe's mass and size. A black hole with the mass of the observable universe would have an event horizon exactly the size of the observable universe. That is not a prediction. That is a measurement, an observation, a fact sitting in the data. The Hubble constant, the number that tells us how fast space is expanding, is about 67 to 73 kilometers per second per megaparsec, depending on which method you use to measure it. That disagreement, the Hubble tension, has been called a crisis. But what if the crisis is not that the two measurements disagree? What if the crisis is that both measurements are correct, and they are measuring different aspects of the same geometry? The cosmic microwave background gives you the global expansion rate, the rate at which the entire interior of the black hole is stretching as you fall toward the singularity. The distance ladder gives you the local rate, the expansion measured within our patch of space-time, a few billion light-years across. If the geometry is not uniform, if there are gradients or inhomogeneities in the way space is curved, the two rates would differ, and they do, by exactly the amount that has everyone confused. The Friedmann equations, the ones that describe how the universe expands, are the same equations that describe the interior of a Schwarzschild black hole when you write them in the right coordinates. The scale factor that tracks the size of the universe grows with time in the same way that space stretches inside a black hole as you fall toward the singularity. The singularity at the beginning of time, the Big Bang, has the same mathematical structure as the singularity at the center of a black hole. The event horizon that bounds the observable universe, the particle horizon beyond which we cannot see, has the same geometric properties as the event horizon of a black hole. These are not loose analogies, these are direct mathematical correspondences. The equations describing our universe and the equations describing a black hole interior are the same equations. The geometries are equivalent. The only difference is perspective. If the Big Bang was not the beginning of time, but the moment we crossed an event horizon, then everything we have been taught about the origin of the universe shifts. The singularity is not the moment creation happened. It is the moment we fell through. The expansion we measure is not the universe growing outward from an explosion. It is the interior geometry of a black hole stretching as we fall inward toward a singularity that has not happened yet. The singularity is in our future, not our past. And when we reach it, billions or trillions of years from now, depending on the exact geometry and the role of dark energy, space-time itself ends. Not because the universe collapses back into a point, but because the geometry that generates the interior runs out. The event horizon sealed us in. The singularity is where the road stops, and there is no way around it. Every path through space-time, every trajectory you could follow, leads there. Not because something is pulling you, because that is the shape of the space you are moving through. The singularity is not a place, it is a moment in the future, and the future is the one thing you cannot avoid. The black hole births universe idea takes this further. If our universe is the interior of a black hole in a parent universe, and if every black hole in our universe spawns a baby universe of its own, then the structure is infinite. An endless chain of nested realities, each one sealed off from the others by event horizons, each one falling toward its own singularity, each one spawning new universes through the collapse of its own black holes. The process repeats forever. Upward and downward, parent and child. There is no top layer, there is no bottom layer. The cosmos is a fractal, self-similar at every scale, reproducing endlessly through a mechanism built into the equations of general relativity. Collapse, bounce, expansion, repeat. That is the engine. And if it is real, then we are not living in the universe. We are living in a universe, one bubble in an infinite foam. One branch on an infinite tree, and every black hole we observe, every stellar collapse, every supermassive black hole at the center of a galaxy, is the seed for another branch we will never see. This is where the philosophy gets uncomfortable. If we are inside a black hole, then we are prisoners. Not in the sense that someone locked us in the sense that the geometry itself is the prison. The event horizon is not a door that was closed. It is a boundary in space-time where the rules change. Cross it, and every direction you try to move leads inward. The future points toward the singularity. The past points toward the event horizon, and the horizon is a one-way surface. You crossed it billions of years ago, at the Big Bang, and you can never cross it again. Information from the outside cannot reach you. Signals you send cannot escape. You are sealed inside a region of space-time that is causally disconnected from everything beyond the horizon. Whatever universe exists on the other side, whatever parent structure we fell out of, is gone, not far away, not hidden behind a veil. It is in your past, separated from your future by a boundary that cannot be crossed. This is not a metaphorical prison, this is geometry. The shape of space-time determines what paths are possible and what paths are forbidden. Inside a black hole, paths that lead outward are forbidden. They do not exist. You can point your spaceship in any direction, fire your engines at full power, and you will still move inward. Not because your engines are weak, because there is no outward. The direction you are trying to move in is not part of the geometry. It is like trying to move north from the North Pole. The question does not pass. The geometry does not allow it. You are confined not by walls, not by forces, but by the structure of space-time itself. And if that structure is the interior of a black hole, then every human who has ever lived, every star that has ever burned, every galaxy we have ever observed, all of it is happening inside a prison we did not build and cannot escape. The word prisoner has implications. It suggests you had freedom once and lost it. But if we were born inside the event horizon, if the Big Bang was the entrance and not a beginning, then we never had freedom to lose. We have always been inside. The geometry we experience, the three-dimensional space we move through, the time we age through, all of it is the interior. We have never seen the outside. We have no reference for what freedom would even look like. A fish born in a tank does not know it is in a tank until someone shows it the ocean. We are the fish. The observable universe is the tank, and there is no one to show us the ocean because the ocean is on the other side of an event horizon we crossed 13.8 billion years ago. The particle horizon, the boundary of the observable universe, is the edge of what we can see. Light from regions beyond that boundary has not had time to reach us. But if the particle horizon is also an event horizon, then it is not just that the light has not arrived yet. It is that the light will never arrive. The regions beyond the horizon are not just far away. They are causally disconnected. No signal from there can reach here. No signal from here can reach there. The boundary is absolute. And if that boundary is the event horizon of a black hole, then the observable universe is not a patch of a larger cosmos that we happen to be able to see. It is the entire interior, the whole structure. There is no outside to look at because the inside is all there is. Or at least, all there is for us. The parent universe, if it exists, is on the other side of the horizon, in the past, inaccessible, gone. This raises the question of fate. If we are inside a black hole, what happens to us? The standard story in black hole physics is that anything inside the event horizon eventually reaches the singularity. The geometry forces it. Time itself points inward. The singularity is not a place you are falling toward. It is a moment in your future, and your future is unavoidable. In a collapsing star, the singularity forms quickly. The core collapses past the event horizon and reaches infinite density in a fraction of a second. But in a large black hole, the interior can last for a long time. The bigger the black hole, the longer the fall. A black hole the size of the observable universe would take an extraordinarily long time to reach its singularity. The interior could exist, expand, evolve for billions or trillions of years before the geometry runs out. Our universe is 13.8 billion years old. If the Big Bang was the moment we crossed the event horizon, then we have been falling for 13.8 billion years. How much longer do we have? The answer depends on what dark energy does. Right now, dark energy is driving the expansion to accelerate. Galaxies are moving apart faster and faster. If that continues indefinitely, the universe enters a phase called the Big Rip. The acceleration becomes so extreme that it tears apart galaxy clusters, then galaxies, then stars, then planets, then atoms. Space-time itself gets ripped apart. That could be the singularity. Not a point where everything compresses to infinite density, but a moment where the geometry becomes so stretched that it breaks. The equations fail, the fabric tears, and everything ends. Alternatively, dark energy could decay. It could weaken over time, allowing gravity to take over again. The expansion would slow, halt, and reverse. The universe would collapse back into a big crunch. That would also be a singularity. A moment when the scale factor goes to zero, density goes to infinite, and space-time ceases to be a well-defined concept. Either way, there is an endpoint, a boundary in time beyond which the geometry does not extend. The singularity is not optional. It is written into the structure. If we are inside a black hole, the singularity is in our future. We are falling toward it. And when we reach it, the universe ends. That is not comforting, but it is also not unique to the black hole interpretation. The standard cosmological model predicts an end too. Either the Big Rip or the Big Crunch, or heat death, where the universe expands forever and fades into cold, empty darkness. Every model has an endpoint. The difference is philosophical. In the Standard Model, the universe is all there is. It began at the Big Bang, and it will end in some far future state, and there is nothing outside it because the concept of outside does not apply. In the Black Hole Model, the universe is a structure inside a larger structure. It began when we crossed a horizon, and it will end when we reach a singularity. The parent universe continues. Other universes exist, sealed off by their own event horizons. The cosmos is larger than we can see, and we are just one pocket, one bubble, one interior region that will eventually terminate while the larger structure continues. Which interpretation is correct? We do not know. We cannot know, at least not from inside the horizon. The only way to tell the difference would be to observe something outside the event horizon, and by definition, that is impossible. The event horizon is a one-way boundary. Information cannot cross outward. We are sealed in. The geometry we measure, the expansion we observe, the cosmic microwave background we map, all of it is consistent with both interpretations. The Standard Model and the Black Hole Model make the same predictions for everything we can measure. They are mathematically equivalent in the regime we can test. The difference is not in the observations, it is in the interpretation. One says the Big Bang was the beginning, the other says it was an entrance. One says the observable universe is all there is, the other says it is one cell in an infinite structure. Both fit the data. Both are consistent with the equations, and we have no way to distinguish them from the inside. So we are left with a choice. Not a scientific choice, because the science does not give you an answer. A philosophical choice. Do you prefer to think of the universe as a singular, unique entity that began from nothing and will end in nothing, with no context and no larger structure? Or do you prefer to think of it as one bubble in an infinite foam, one branch on an infinite tree, born from the collapse of matter in a parent universe and destined to spawn baby universes of its own through the black holes it creates? Both stories fit the math. Both are allowed by general relativity, and both leave you with the same uncomfortable conclusion. You are confined to a finite region of space-time. You cannot see beyond the horizon, you cannot escape the geometry, and you are falling toward a singularity you will eventually reach. The word prisoner might be too strong. It implies captivity, constraint, loss of freedom. But what if you were never free to begin with? What if freedom, in the sense of unlimited access to all of space-time, is not a thing that exists anywhere in the cosmos? Every observer, in every universe, in every black hole, is confined to their local region, their observable universe, their causal patch. The boundaries might be different, the size might be different, but the confinement is universal. Geometry imposes limits. Event horizons impose limits. The speed of light imposes limits. No one gets to see the whole structure. No one gets to step outside and look at the cosmos from an external vantage point. Every perspective is an interior perspective. Every observation is local, and if that is true, then calling us prisoners is missing the point. We are not imprisoned by the geometry. We are part of it. The geometry is not a cage, it is the stage, and the play only makes sense from within the stage. Step outside, and there is no play. There is no stage. There is just a different geometry, with different limits and different observers confined to their own patches, asking the same questions we are asking. Humanity's place in this structure, if it is real, is not special. We are not at the center. There is no center. We are not at the top or the bottom. There is no top or bottom. We are one branch on an infinite tree, one bubble in an infinite foam, one interior region in an infinite chain of nested black holes. The cosmos does not care about us. It does not care about anything. It is a geometric structure that evolves according to the equations of general relativity. Matter collapses, event horizons form, interiors expand, singularities terminate, black holes spawn new universes. New universes spawn new black holes. The process repeats forever. And we are here, now, in this moment, observing this patch of space-time, because the geometry allowed us to exist. That is all. There is no deeper reason, no purpose, no design. Just geometry playing itself out, producing structures that are capable of observing themselves, and we happen to be one of those structures. But even if our place is not special, our ability to ask the question is. Out of all the possible configurations of matter and energy in this universe, a tiny fraction of them are capable of thought, of curiosity, of building telescopes and writing equations and tracing the expansion back to its origin and asking whether that origin was a beginning or an entrance. The fact that you are reading this, the fact that these words exist, is a consequence of a chain of events that started with the collapse of a star in some parent universe billions or trillions of years ago. That collapse formed a black hole. That black hole spawned our universe. Our universe expanded, cooled, formed stars, formed planets, formed the conditions for chemistry and biology. And out of that chemistry and biology came brains capable of looking up at the sky and wondering what the hell is going on. That is not nothing, that is extraordinary. The cosmos is mostly empty space and radiation and dark matter that does not interact with anything. The fraction of it that has organized itself into self-replicating molecules capable of processing information and asking questions is vanishingly small. And yet here we are, not because we are special, but because the geometry allowed it. The parameters of physics, the constants that determine how forces work and how particles interact, fell into a range that permits complexity. Stars form, planets form, life forms, intelligence forms, and intelligence asks questions. That is what we are, a patch of space-time that has become aware of itself, a configuration of matter that can look at the equations and see that they describe the structure it is part of, a branch on the tree that has figured out there is a tree. The math tells us we might be inside a black hole. It tells us the observable universe has the size and mass of a black hole interior. It tells us the expansion we measure matches the geometry of space falling toward a singularity. It tells us the Big Bang could have been an entrance, not a beginning. It tells us every black hole in our universe might spawn a new cosmos, sealed off by an event horizon, evolving independently, unreachable and unseeable from here. The numbers line up, the equations allow it, the geometry fits, but the math does not tell us why this matters. The math does not care. Equations do not have opinions, they just describe. The question of what it means, the question of how we should feel about living inside a structure we cannot escape and cannot fully understand, is not a question physics can answer. That is philosophy, that is psychology. That is human. And the human answer, the honest one, is that it is terrifying and beautiful at the same time. Terrifying because it means everything we thought we knew about where we are and how we got here might be wrong. The universe is not all there is. The Big Bang is not the beginning. We are sealed inside a geometry that will eventually terminate, and there is nothing we can do about it. We are falling toward a singularity, and the geometry does not give us a choice. That is the prison. That is the constraint. We are passengers on a ride we did not choose, moving through a structure we did not build, heading toward an endpoint we cannot avoid. And no amount of knowledge, no advancement in technology, no breakthrough in physics will change that. The geometry is what it is. The equations are what they are, and we are bound by them. But it is also beautiful because the structure is so much larger than we imagined. If we are inside a black hole, then the cosmos is not just the 93 billion light-years we can see, it is infinite. An endless tree of universes nested inside black holes, nested inside universes, each one a variation on the theme, each one evolving according to the same fundamental rules, each one producing observers who look up and wonder whether they are alone. We are not alone. We are one branch among infinite branches, one universe among infinite universes. The parent universe is out there, on the other side of the event horizon, continuing to exist and evolve while we fall through its black hole. The baby universes are in here, inside every black hole we observe, expanding and cooling and forming stars of their own, completely unaware that they are nested inside a structure we are part of. The cosmos is alive with creation, endlessly reproducing through the mechanism of collapse and rebound, and we are part of that cycle. Not the center of it, not the purpose of it, just part of it. A pattern in the geometry, a fluctuation that became aware, a branch that learnt to see the tree. If the numbers are right, if the geometry is what the equations suggest, then we are living in a hologram projected from the event horizon of a black hole, a three-dimensional cosmos generated by two-dimensional physics on a boundary we can never reach. Space itself is not fundamental. It is emergent. Time is emergent. The distances we measure, the volumes we calculate, the clocks we watch, all of it is a projection from information encoded on a surface 46 billion light-years away. The horizon contains us, defines us, generates us, and we will never touch it, never see it, never confirm that it is there. We can only infer it from the math, from the entropy, from the fact that the observable universe has exactly the size and mass a black hole would need to produce the geometry we measure. That is the only clue, and it might be the most important clue physics has ever given us. So what do we do with this information? What does it change? In practical terms, nothing. The sun still rises, gravity still pulls, stars still burn. The equations that describe how matter moves and how forces act are the same whether we are in a standalone universe or inside a black hole. The technology we build, the experiments we run, the observations we make, none of it depends on which interpretation is correct. The standard model works. The black hole model works. Both describe the same reality from different perspectives. The choice between them is not a scientific choice, it is a philosophical one, and philosophy does not change the trajectory of a photon or the collapse of a wave function. It just changes how you think about it. But thinking about it matters. It matters because the question of where we are and how we got here is not just an academic curiosity. It is a question about meaning, about context, about whether the universe we observe is all there is, or whether it is part of something larger. The standard model says the cosmos is unique, singular, all-encompassing. It began from a singularity, and it will end in some far future state, and there is nothing beyond it, because beyond is not a concept that applies. That is a lonely picture. It makes us the only show in town, the only observers in a cosmos that has no context and no larger structure. We are it, and when the universe ends, we end with it, and there is nothing else. The black hole model says the opposite. The cosmos is infinite, endlessly reproducing, filled with nested universes spawned by the collapse of matter in other universes. We are one branch on an infinite tree. The parent universe continues, the baby universes exist, the structure is eternal, it has no beginning and no end, it just is, and we are part of it, a small part, a temporary part, but part of something vastly larger than anything we can observe. That is a bigger picture. It is not necessarily more comforting because it still ends for us, but it is more connected. We are not alone. We are not unique. We are part of a process that has been running forever and will keep running forever. And that process does not depend on us. It does not need us. It does not care whether we understand it. It just keeps going. The equations allow both stories. The observations fit both stories. And we, standing here at the beginning of the 21st century, with telescopes powerful enough to see the cosmic microwave background and particle accelerators powerful enough to probe the Higgs boson and gravitational wave detectors sensitive enough to hear black holes collide, we still cannot tell which story is true. Maybe we never will. Maybe the question is not answerable from inside the horizon. Maybe the only way to know whether we are in a black hole is to somehow get outside it, and the geometry forbids that. The event horizon is a one-way surface. Once you are in, you are in. There is no exit. And if the Big Bang was the entrance, then we have been inside for 13.8 billion years. The door closed a long time ago, and it is not opening again. So we are prisoners of geometry. Not because someone locked the door, but because the door is a feature of space-time itself. The boundaries that confine us are not walls we can break through. They are the shape of the space we live in, and that shape, according to the math, might be the interior of a black hole. The observable universe might be a bubble, sealed off from a larger structure by an event horizon we crossed at the Big Bang. Every direction we look, every measurement we make, every photon we detect, all of it is happening inside that bubble. And the bubble, for all we know, is one of infinite bubbles, each one spawned by a black hole in a parent universe, each one destined to spawn black holes of its own, each one falling toward a singularity that will end its existence while the larger structure continues. That is the picture the numbers are painting. And if the picture is right, then we are not just living in the universe, we are living in a black hole, and we have been since the beginning. The geometry defines us, confines us, and eventually it will end us. That is the price of existence. That is the shape of the cosmos, and there is no escape. Just the slow, steady fall toward a singularity we will reach one day, billions of years from now, when the geometry runs out and space-time itself comes to an end. And the only question left is whether we will understand where we are before we get there. You wake up, you go to work, you eat lunch, you check your phone, you look up at the sky, and it looks the same as it did yesterday. The ground beneath your feet feels solid, the air around you feels still. Time moves forward at the pace it always has. Nothing about your morning coffee or your evening commute or the conversation you had last Tuesday suggests that you are falling, and yet the math says you are. It says you have been falling since the moment the universe began, not through space, through space-time itself, toward a boundary you will never see coming because it is not a place, it is a moment, and that moment is in your future. The size of the observable universe matches the size of a black hole with its mass. The expansion rate we measure matches the geometry of a black hole interior. The singularity we think is behind us could just as easily be ahead of us, and every equation we use to describe where we are and how we got here is the same equation that describes the inside of an event horizon. Those are not interpretations, those are measurements. The coincidence is either the largest fluke in the history of physics, or the universe trying to tell us something we have been too uncomfortable to hear. We may never know which interpretation is correct. The geometry seals us in. The event horizon, if it exists, was crossed 13.8 billion years ago. There is no going back, no looking outside. No way to confirm from the inside whether the boundary is real. We are confined to this patch of space-time, this bubble, this interior, with no access to whatever lies beyond. And if we are inside a black hole, then so is everyone who has ever lived. Every thought you have had happened inside. Every star you have ever seen burned inside. The entire observable cosmos, with its 100 billion galaxies and its trillions of stars, exists in a region of space-time that may be nothing more than the interior geometry of a collapsing object in a universe we will never see. That should bother you. It should make you stop and think about what it means to exist in a place you cannot leave, moving toward an end you cannot avoid, sealed inside a structure you did not choose and cannot escape. But it should also make you realize that the cosmos is so much larger, so much stranger, so much more deeply layered than anything our intuition prepared us for. If we are inside a black hole, we are not alone. The tree branches forever, and somewhere in another interior, in another universe nested inside another black hole, someone else is looking up at their sky and asking the same question we are asking. Are we trapped, or are we just part of something bigger than we ever imagined? The math does not answer that. It just shows you the door, and the door is behind you. You already crossed it.